I have to make it like this.
Любую счетной степени. Как в карте вариант эксперт.
Okay, everyone, let's get started. Welcome back at the fourth day of this Superconductivity school. We're going to start our series today with the final lecture by Professor Agterberg.
Okay. So good morning, everyone. So I think the last lecture was perhaps the most technical of all of them. And so what I tried to do right now is just summarize the key points here. And so what we're trying to do is build tight binding models. And so what I told you is that these tight binding models are defined by the space group and then the Wyckoff position within that space group. And then once we have a Wyckoff position, we have a site symmetry for that Wyckoff position. And then we need to define an irreducible representation of that Wyckoff site symmetry. And so what I wanted to do using this group information was build a basis for the tight binding model. And to do that, we said we can take our space group and we can break it up into the site symmetry times the translation group. And here we're dealing with 2 dimensions. And we can then break the group into a series of sets where each set is described by a coset representative. And those coset representatives simply move us between 2 sublattices or the number of sublattices we want. So the problem we were focusing on was s orbitals in space group 123 on Wyckoff position 2f. Okay. And so we only had in our case 2 of these coset representatives, the identity, which brings the atom to itself, and then the C4 symmetry, which rotates from atom 1 to atom 2. All right, so with those definitions, we can write down our basis. We choose a 0 site. So we said, let's say this is our 0 site. This is site index 1, and then orbital I. But as we've pointed out already in this problem, all the orbital representations are one-dimensional, which makes life a little bit easier. But we have here an s orbital here, and then we can generate any other site in the lattice by first applying the coset representative to get us to the right sublattice. So we can go from 1 to 1 or from 1 to 2, and then applying a translation symmetry, and that'll generate our entire tight binding lattice. Okay. So that's how we defined our tight binding lattice. And then we asked the question, how do space group symmetries operate on this tight binding lattice? And if you remember the notation, this space group symmetry is a rotation vector, or a rotation which we call P, and then a translation which we call V, but the P is what we have to remember here. And we showed that it has this particular form where, importantly, we have a matrix U that doesn't depend on the positions R and R prime, the lattice vectors, but do depend on the orbitals and on the sublattice components. All right, and so then we said, okay, we have this matrix, and we constructed that matrix for a few examples. Actually, just one example, actually 2 examples. And actually, a minor error was in one of the examples that showed up last class that was pointed out to me. So I'll correct that soon, but it doesn't change anything for any of the homework you're doing, for example. All right, so we constructed some of these U's. And then we said, now let's go to the tight binding basis. So we exploit the translational symmetry of our hopping parameters. And then we go to Fourier space. And what I pointed out there is that everything works nicely if we make a particular choice for this Fourier space. In particular, we make sure that we add the position of the sublattice site in the Fourier transform. And I showed you an example where we did a tight binding where we added this, and a tight binding where we didn't add this. And you could see that the tight binding where we added this looked much simpler than when we didn't add this. All right, so with this particular choice, we had a small cost, and that cost was that our Hamiltonian was not invariant under k goes to k plus reciprocal lattice vector. And so in particular for off-diagonal matrix elements, meaning in sublattice space when we're hopping from one sublattice to another, we can pick up phase factors in our problem of -1. Okay. So, but that didn't matter for the eigenvalues. The eigenvalues still have the full symmetry of the reciprocal lattice like we expect. All right, and then, so that was one constraint we had on our Hamiltonian. And then we had a second constraint on our Hamiltonian, and this is where this matrix U played a role. This particular matrix U, which we called UG, it shows up very nicely here, and we don't have to, and what mattered was this does not depend on R and R prime. So this matrix UG is not dependent on K, and so we can take the matrices we derived here and use them here. All right, and so the transformation rule under a space group symmetry is we identify this matrix U, and we also have to rotate the vector K by this rotation vector P to the -1. And so what we were doing then is we were applying this to this particular example, and we'd pretty much finished with the non-spin orbit part. But what I didn't do was add spin orbit to this and show you how we do that. But let me go back to that now, and I'm going to see if I can get this to work like I want. So I'm going to put this on the side projectors and then turn this off. And then go to the blackboard. Okay. I don't know, does this help actually with seeing the blackboard better? It does here, I guess, but maybe not over there. Okay, well, let me go back to where we were. Okay. All right, so again, so that was our sublattice choice. Yeah, there is, I think this should do it, but it doesn't seem to work very well. This, yeah, so I think there's something wrong with that. But, okay. Okay, so we're putting s orbitals on here. We're trying to write down a tight binding Hamiltonian. And what I told you last class is that we need to identify all the generators of the space group to do this. And we'd written down these U matrices for these generators. And yeah, so so these generators, well, let me tell you what those U matrices are, and then I'll show you what my error was. Okay, so there's, yeah, these are all okay. All right, so C4 was the element I used to go from one sublattice to the other. And then we showed that all these U matrices are tau 0 for basically every element in the site symmetry group. And it's actually tau x for any element that switches the two sublattices. Okay. Okay, and now let me put my correction in. So the correction is the following. So if you remember, I acted C4 on one basis element and another basis element. And when I did that, I extracted a matrix for the representation. What I extracted was actually the transpose of the matrix, not the matrix itself. And the reason is simply that when we define an irreducible representation, so when we go from basis element I, we apply G. Then the matrix elements are defined this way. And so if you look back to the lecture, you'll see that in practice, this means I should have been writing the transpose of what I was writing down as my matrix. So this U, this row is the matrix U, and I've been writing IJ as opposed to JL. Okay, so just a minor comment. It doesn't change actually anything of what you're doing, but if you're confused by it, you can see I made an error. All right, so back to the tight binding problem. So we argued then that H of K without spin orbit coupling. Can be expanded in these sublattice matrices. And so we have 4 functions that we have to identify. And then I argue that we can identify the symmetry of these tau I matrices. And the idea is simply I can apply these matrix elements to it so I can see what, say, U tau I U dagger looks like. And then for each element G, I can see that this takes us to either plus or minus tau I. And then this gives me the characters in the group D4H. So I do this for every element G. And when I look at all the characters, I can see that I can identify which irreducible representations the tau matrices belong to. And so what I told you is if you carry this out, and I think, yeah, we even illustrated it. So we said tau 0, tau x, they belong to the A1G representation. And tau y, tau z, they belong to the B2G representation, and then this B2G looks like cos kx minus cos ky. Okay. All right. Okay, so where we stopped last class then is I told you the form of the Hamiltonian is this. Right. So this is pretty much where we stopped. And here you see that 3 functions are showing up. The tau 0 term, the tau x term, and the tau z term. And there's no tau y. And at the very end of the lecture, I explained why tau y doesn't show up. But I'll go over that in a little bit more detail because I did that pretty quickly. But here you can see the 2 rules that we have on the side being implemented. So for tau 0 and tau z, we do have that the Hamiltonian must be invariant under k goes to k plus g. And what that means then is that we can only have integral multiples of kx and ky showing up. For tau 0 and tau z then, we don't have these factors 1 over 2, but we just have this. And in practice, we can add more terms here. So I can add cosine 2kx plus cosine 2ky. I can add another term, which is cosine kx times cosine ky. But the philosophy here is we want to include all terms allowed by symmetry. So we have all the operators included. And as long as we have something that's non-zero there, our theory captures many of the properties we need it to capture. Okay. And it was also pointed out that this term allows a constant, for example, a mass term or a constant. So, but that constant is like a chemical potential, so I didn't include it here. Okay. And then also, so these 2 have to be periodic in the reciprocal lattice. This term is basically anti-periodic in reciprocal lattice vectors gx and gy. And that's why these factors of 1/2 show up here. So tau x and tau z will always have these factors of 1/2. And then tau z and tau 0 will always have these others. But I can multiply this just if you want. You can multiply this by a term, say cos kx times cos ky. If you want to include other terms, this still satisfies the correct periodicity. Okay, so just giving you some idea of the structure. All right, so now let's go back to why tau y doesn't show up. All right, so tau y doesn't show up because we introduced time reversal symmetry. And here, because we have no spin, time reversal is just the complex conjugation operator. And the key point was that if I look at tau y under time reversal, what happens to it? It goes to minus itself. So it picks up a minus sign. But what I didn't carefully show last class and is useful to show is we also have our symmetry rule under a transformation. So this symmetry rule, and I'm going to apply it to inversion because inversion was a simple tau zero matrix. So we have the condition that inversion, HK inversion to the -1 must equal H of minus K. So that's just the symmetry rule. Our matrix is just the identity matrix. And so this tells us right away that all the Fi of K must equal Fi of minus K. And then if you look at the tau y term, you find that the tau y term, this implies that Fy of K must equal Fy of minus K. And again, that's because time reversal takes K to minus K, so we get a rule like this, exactly like this, but with time reversal written down. And so the condition that this is odd under time reversal and that we have, sorry, time reversal implied this minus sign, combining this and this together tells us this term must be 0. So that's why tau y doesn't show up. It's because we have inversion and time reversal together. Okay. All right, so that's the Hamiltonian without spin orbit coupling. Just make sure I didn't forget anything. So now let's add spin orbit coupling. Okay. So I'm just going to call this SOC in many places. So the philosophy here is a little bit different than most type binding approaches. Most type binding approaches, you identify the hopping parameter, and then you put that in by hand and derive the type binding. We're trying to use a more general symmetry approach to say what is the general form of the type binding. And so to do that, the key step was we identified the symmetries of these operators tau I. And so now what we're going to do is the same thing. We know that if we add spin orbit coupling, I'm going to have an additional term in my Hamiltonian, which I can maybe write like this. So I'm going to have products of tau I and sigma j, but here j is just x, y, z, so just the 3 spin components, because implicitly here I've included sigma 0 everywhere. I've just set that to 1, right?
Ask me a question.
Yeah.
So, and if inversion is broken,
Yeah,
then tau y does not need to be 0.
that's true. Yeah, so no,
It's
it's so this is a great question. Actually, the symmetry that really matters in this case is time reversal times inversion. No, you're right. You're right. So if inversion is broken, tau y terms can show up in the Hamiltonian. No, you're absolutely right. Actually, yes. Oh, yeah. There's more details I can say about that, but okay, we can talk about it separately. Yeah. So, okay, I'll leave this for now. Yeah, this is without spin orbit coupling. Now we're adding spin orbit coupling. Okay, so here J is just X, Y, Z. The 0th component has already been included here. And so now we want to figure out what are we allowed to do for these lambda ij of k. And again, we're going to apply the same approach. In D4H, I can identify the symmetries of these Pauli matrices. So in D4H, which is our point group, sigma x, sigma y, they belong to this EG representation. And sigma z belongs to the A2G representation. Okay, so I can just go to the character tables and look that up. It makes sense that this forms a 2-dimensional representation because if I do a 4-fold rotation, I go from X to Y, so they're linked, right? And so I know the symmetries of these again, and the construction here of the Hamiltonian is just the condition that the Hamiltonian must be invariant under all the point group operations. And so now I want to start multiplying all these terms. I know the symmetries of these. I know the symmetries of these. I can figure out what k dependencies are allowed to multiply these terms. Okay. All right, so there's a couple additional conditions. Inversion is even under, spin is even under inversion. And so just as here before, we're going to get the condition that lambda ij of k must equal lambda ij of minus k. So that's from inversion symmetry. In addition, from time reversal symmetry. So here, time reversal, the spins are odd under time reversal, spin flips under time reversal. So here, sigma alpha goes to minus sigma alpha. And so you can see the time reversal constraint is going to be different for the different taus. For tau 0, tau x, and tau z, this is time reversal invariant. And so for tau 0, tau x, tau z, we're going to have lambda ij of k equals lambda ij of minus k, because time reversal will flip this, but not that. And you can see, oops, minus sign again. So you can see that for these operators, we can't have any tau dependence showing up in the Hamiltonian. Is that clear? Tau 0, tau x, tau z don't change sign under time reversal. Sigma changes sign under time reversal. So under time reversal, lambda ij of k goes to lambda ij of minus k. And for these three tau operators, this is this must pick up a minus sign because of the oddness of this under time reversal. Yeah.
Tau represents this particle whole thing, right?
No.
Particle
Tau is again the sublattice. Sublattice, yeah. Yeah. It's always here. I'm only talking about HN. There's no superconductivity. Okay, so
I think this is just a quick question.
yeah.
Generally, when we talk about Prokofiev, usually inversion symmetry is broken. Are we assuming still inversion symmetry in the system?
Yeah. So throughout, everywhere time reversal and inversion are properties of the normal state. So inversion symmetry is here and time reversal is here. And I've represented inversion symmetry by this operator. Okay. So this tells us that the only term that shows up in the spin orbit coupling is tau y. Okay, and now we can ask, well, we know the symmetry of tau y. It's B2G. We also know the symmetry of all these spin operators. So, and I'm going to tell you off the bat that we can't write down any momentum dependent functions in 2-dimension that have this particular symmetry. And what that means is we rule out this. Sigma x and sigma y can't show up. I'm not telling you the details. I'm just telling you there exists no 2D momentum functions that transform as sigma x and sigma y. And the way to see that is the simplest momentum functions are kx times kz and ky times kz, but kz should be 0, right? So these are not allowed to show up. And so the only term that shows up, in fact, is lambda tau y sigma z. And then what we need to do is get the right momentum dependence of the function that multiplies this. And we can get that by identifying this as B2G. This is A2G. And the product of these two is B1G. So I need to have some B1G momentum dependence. And just to remind you, that is same as the product of kx times ky. And so is anyone willing to take a guess what that function might be? Not that straightforward, but maybe. We've got many people here. Sorry? I heard a guess. Okay, well, you've thought about it long enough. The appropriate momentum function is this. You can see this transforms as kx times ky. We also have a tau y, so we have to have these halves showing up. And so this is our spin orbit coupling. Yeah?
So this is the next nearest neighbor hopping, right?
This is actually a nearest neighbor hopping between the sublattice. Because it has this kx over 2, ky over 2, that tells me it's coming from this. But then it has the signs, and so you have to think about where those come from. In my opinion, it's much easier to write down spin orbit coupling terms this way than actually going through, people look at the gradient cross sigma and then try to write down hopping terms to see which kind of real space hoppings. Writing it directly in momentum space, I think, is much easier. All right, so this is our spin orbit coupling. Okay.
And B1G because you had the B2G and
Yeah, we had an A2G times a B2G, and that product is B1G. Yeah. Okay. All right, so let me see if I actually have. Okay, I do have the full Hamiltonian here. Okay, this is homework question 3, which is also in the notes from yesterday. Homework question 3 is to reproduce this for px orbitals, right? And then I added a little bit about altermagnetism, but in addition, that just means adding another term to the Hamiltonian. And I'll talk a little bit about that in a second. But here's the full Hamiltonian. And so now what I want to do is focus on one term in that Hamiltonian, because I want to get to one other useful result. So I want to look at this term. So I'm going to talk about this application to altermagnetism in a second, but I'm going to focus on this term. And now I'm going to expand. I'm going to say, let's consider K points near the M point. So let's consider carrying out an expansion near the corner of the Bruin zone where I expand in delta Kx and delta Ky. Well, then this term becomes just like delta Kx, and this term becomes like delta Ky. So if I write this term out, okay, this will become T1 over 4 tau x delta Kx times delta Ky. So near the M point, this is our dispersion. Okay. All right, so this is all fine. But what I want to point out now is that if I use the same, so imagine I started from a very different point of view. Suppose I wanted to derive a Hamiltonian that is valid near the M point itself. And then I want to use the same arguments. I want to assign some operators, some symmetries, etc. You can see that something strange has happened here. So here I have tau x multiplying delta Kx times delta Ky. And if I want this to be an invariant, my conclusion is that this tau x should be B1G symmetry, right? But that's not what we got from the real space picture, or tau x was A1G symmetry. So where is this difference coming from? And how do we solve this when we start trying to do small k expansions around points? Right, and so here, the solution is buried in, this is something, okay, maybe people who are more familiar with this will appreciate, but I'll at least tell you where it comes from. So the key is that when we're talking about finding a Hamiltonian near the M point, then we're not actually dealing with the real space picture, we're dealing with momentum space pictures. And then what we need to find are so-called representations of the little group at M, okay? And the little group is defined by the set of space group elements that keep K unchanged up to a reciprocal lattice vector. And in what we've been doing, if we have a non-zero reciprocal lattice vector that shows up in this expansion, so many cases, all these reciprocal lattice vectors are 0, and then this complication doesn't arrive. But if a reciprocal lattice vector does show up, then we have the issue that our UG does not actually commute with H of K. So this is this minus sign I was telling you about before. So if you remember, we wrote down, so UG, HK, UG takes us to K plus G for the elements for which G is non-zero. And then that tells us that we have to introduce this, what I called gauge matrix V of G to show up. And what that means in practice is in momentum space, we're not looking at these U matrices directly, but we need to look at the product of this phase factor for non-zero reciprocal lattice vectors times UG. These commute with the Hamiltonian. And because these commute with the Hamiltonian, our rules from identifying irreducible representations say that we should consider these objects, not the original UGs themselves. Right? So maybe a bit quick, but what that means in the end is we can use this information and you can actually deduce all the little group characters from this object here. But again, this matrix is VG times UG. So if we were working in momentum space directly, it's not enough to know this. We have to calculate this. And so what I'm going to do now is for the C4 element, calculate this VG and show you how it changes because of that. And because of that, this tau X matrix picks up a different symmetry. Okay. So at the endpoint then, we're not going to represent C4 by the matrix U, but instead, we're going to represent it by some VG UG. This we already know. This we said was tau X. Now, at the endpoint, we need to find all the space group elements. That preserve M up to a reciprocal lattice vector. And so now if I look at pi pi, and I do a C4 rotation on pi pi, what's my resultant vector? It's pi minus pi. Yeah. And this is equal to pi pi minus 0,2 pi. And so the reciprocal lattice vector for G is non-zero. And so now I need to compute this matrix V of G for this reciprocal lattice vector. And so I need to know the positions of our two sites. And that was our choice. R1 is 1/2 0, R2 is 0 1/2. And so then our matrix VG, well, this has no inner product with this. So that component is 0. This is a purely diagonal matrix. This component has an inner product with this, and that inner product is e to the I pi. So that's a factor of -1.
It's V of M. Yes.
Sorry?
This is V of M.
Yeah, this is V at the endpoint. So we're imagining that we're trying to build a theory around the endpoint and seeing what comes out. And so now you see what happens. This is now represented by VG times tau X. And that matrix is tau Z, tau X. And so that is I tau Y. So our C4 representation is now I tau Y. And you can actually go and see if this is right. So if everything we did is right, let me see if I can get this to work. We should be able to go to the Bilbao crystallographic. Oops. Okay, well, maybe it's better to look on the sideboards. All right. So what I'm going to see is I'm going to go to this space group 123 and see if I have a representation in which my fourfold rotation is represented by this matrix. All right, so I'm going to go to Bilbao. I'm going to look up representations. I'm going to be looking at space group representations. So I'm looking at representations of the space group. I'm going to enter my group 123, look up irreducible representations for that group 123. We're looking at the endpoint. So I'm looking at representations at the endpoint. They're going to be all pulled up for me now. And we're going to look at the element C4. So that is this element here. And I'm looking across here to see if anywhere I have a representation where this is represented by I times tau Y. And I get something that's almost right. So you can see that here I get something that is minus I times tau Y. So there's an overall minus sign that shows up. And when I was planning this for a lecture, I was a little concerned about that minus sign, but I know where it comes from. it comes from the fact that the basis that Bilbao uses, what I call 1 and 2 is not what Bilbao calls 1 and 2. They call it 2 and 1. And because of that switch, that's where the minus sign comes from. So you get exactly the same matrix, and it turns out that's the representation that shows up here. So computing what I showed over there will give you what shows up in the Bilbao crystallographic server for those representations. Okay, good.
Didn't we rotate the clockwise instead of counterclockwise?
Sorry?
Didn't we rotate clockwise instead of counterclockwise? But pi pi's, which they might denote by plus
Yeah, the counterclockwise is this.
pi
Counterclockwise
would be
right?
Yeah.
minus pi.
Minus pi.
We rotated in the minus direction.
Yeah,
There it has a minus.
yeah, you would. It would be because you switch the reciprocal lattice vector from 0 2 pi to 2 pi 0, and that gives you that tau z becomes minus tau z.
Yeah.
Yeah, so that, yeah, so, okay, it could be this as well. Yeah. Okay, I mean, okay, but, okay. All right, good. So later, I'm going to talk about this change.
VM is diagonal.
Yeah, this matrix is diagonal. Yeah. Yeah, but now I have to use the original UG we had before, so it's the product of these two. Yeah, so this is tau z. Okay, that doesn't look like an X, but it is an X. Is this? Yeah. Yeah, so that's why I get this I tau I. Okay, so this is going to show up a little bit later when I talk about the violation of Blount's theorem. And in particular, I'm going to have a matrix defined in real space, and you're going to see it's going to look different when we go to K-space, but that's because we're implicitly doing an expansion in K-space like this. So when we consider momentum space representations, we can get this change in the form of the operator that represents it because of our choice of Fourier basis. That's where this comes from. Okay, good. So let me go back to putting this in. Okay. Yeah, so the main formula here is actually this formula. And by the way, this portion here comes because the space group operations has a translation part V. So it must pick up this phase factor from that. Okay. Whoops. All right. So what we've done is we've derived a tight binding Hamiltonian or s orbitals on this on space group 123. And so that's nice, but we want applications of this Hamiltonian. And so now what I'm turning to is applications of these kinds of tight binding Hamiltonians. And I've chosen applications where the specific Hamiltonian actually gives rise to physics that is beyond the specific Hamiltonian. And I thought I was going to have plenty of time to do altermagnetism, but as you can see, I don't have time to do it all. And so what I'm just going to tell you is that this Hamiltonian that we just derived, it's if we add to it altermagnetism, so here if we add to it a term J tau z sigma z, what this means is on the two sublattice sites, we have a spin that's up in the z direction. On the other side, we have a spin that's down, because tau z is plus minus, and that is actually an altermagnet. So, I mean, so in some sense, you can trust me on that, but we can add this term to our Hamiltonian, and we can ask, what are the properties of this Hamiltonian? And it turns out you can show that this Hamiltonian, if you look at the band structure for it, and here's the band structure, so we have two lower bands and two upper bands. If the chemical potential sits in this gap here, then quite generically, you have a two-dimensional mirror Chern insulator. All right, and so there is a quick application of this, and you can find that out in this paper here. So I have to highlight this because Jorn Venderbos sent me all his PowerPoint slides because I thought I was going to go through this in detail. And so for that effort, I should certainly highlight what he's done in this context. And what do we mean by a mirror churn insulator? Well, what we mean is you can calculate the churn number for spin up electrons and spin down electrons. And it turns out in these two bands here, that churn number is opposite. So it's +1 for, say, spin up, -1 for spin down. But then you can calculate a number that's the difference between these two, and that's called the mirror churn number, and that is quantized. And that means that if you sit in this gap here, you will have edge states associated with that. All right, so that was very quick as the application. And this model, by the way, is often called the Lieb lattice model for altermagnetism. So if you see that discussed, you've derived the model. Okay. And in addition, if you want more applications to altermagnetism in kind of similar models, Mircea Roig, who is here, has developed a whole series of these for altermagnets, and so you can see how it applies. So that's, I think, all I'm going to say about altermagnetism. But just to tell you, there is an application of these models to altermagnetism, and it gives rise to some non-trivial results. All right, so now I'm going to switch to models that are relevant for superconductivity. And so now I want to switch space groups from the nice space group 123. I'm going to switch to space group 129, which isn't quite as nice because this is a non-symmorphic space group. And so what I mean by that is we can look at the elements that generate this space group. And here I've written them all down. But you notice, okay, I have the same translation symmetries as in space group 123. Now I have a series of rotation elements, and these are the same rotation elements we wrote down before. But previously, we always had a 0 in the translation sector multiplying, or here. But now you can see that only the inversion has no translation following it. All these other elements have fractional translations following it. This is called non-symmorphic. It's not possible to choose all the translation parts of these operators to all be 0. If it's not possible to do that, it's a non-symmorphic group. Okay. All right, but we can still apply the same formalism. Nothing is any different. We don't care if it's symmorphic or non-symmorphic. We can still derive these matrices U, and we can write down a tight binding Hamiltonian. And just to give you a feeling of how you might do that, it turns out in iron selenium, we are actually interested in the 2A Wyckoff position. So this is going to apply to iron selenium. It actually also applies to cerium, rhodium, to arsenic too, but that's actually at a different Wyckoff position. So the Hamiltonian is slightly different, but qualitatively things will be the same. So I'll talk about where it applies there and also about iron selenium. And then this form of Hamiltonian with these non-symmorphic elements actually tend to apply to a lot of superconductors. So many heavy fermion superconductors have features like this. And it turns out the Fermi surfaces sit in the right area for these features to be important. Okay. All right. So, but let me just run you through how we do this. So we have the 2A Wyckoff position, and you can go to Bilbao and look up what those coordinates are. It's 1/4, 3/4, and 3/4, 1/4. So I've drawn those here. I'm going to put x² minus y² orbitals on these sites. It's not going to matter too much which orbital that shows up, but we can do that. And this is in mind, I have iron selenium, in monolayer iron selenium as my test case. And so this matters for monolayer iron selenium. And here's the monolayer iron selenium lattice structure. The reds are the irons, and then the seleniums are shown in yellow. And you can convince yourself that, well, you have to look at it for a while, but you can convince yourself that if you put the origin at the inversion site here, then these elements are symmetries of your space group. But that takes some work. Okay. All right, but the key thing is that I need to choose my coset representatives. And so here is my coset representative. I want to figure out what takes me from 1 to 2. And with a little bit of work, the inversion is sitting here. So you can see that if I do an inversion operation, I'll go from 1 to here, and I do a translation like along the 1, 1 direction, I come back to 2. You could have put an inversion here right between these. There is an inversion directly between the two sites. So it's clear it should be the coset representative that switches the two sublattice. A natural choice is inversion times some translation, okay? And again, the translation part doesn't matter when we find these matrices. And so now we can go through the same process. I've defined this way. So I defined the second site as inversion applied to the first site. Now I can apply inversion to the second site, but inversion squared is just 1. And so I get the same matrix back. And that tells me right away that the inversion operator is represented by tau x here. Okay, so that's the matrix we'll be using. Okay, I'm sketching it. So, but you can also show then as you go through the other generators that C4 is tau x, MX is tau 0, MZ is tau 0. Yeah.
That is picture. Where is the center? Like here you chosen some center, right? In that.
Yeah.
That is picture. Where is the center?
This center.
Yeah,
Okay, you're making me think. Okay, so here's a unit cell. Yeah, okay. Maybe the center is here. You can double check me.
Like on the diagonal and between the.
Yeah, so between two irons, I have to check.
Okay,
So
okay.
specifically, it's at an inversion site, but there's a couple inversion sites in the structure. So
How do you understand this position 1, 4, 3, 4 across?
this is the choice made in Bilbao. So
Okay.
I'm trying to use their conventions. Yeah.
Yeah.
So I'm just sticking, and then they put the inversion here. So you need to figure out an inversion that has this, and then you need to choose your unit cell the right way to put those in there. So this is even not the right unit cell, right? The unit cell should do something like that. So it takes, yeah, good question, but something you can figure out yourself. All right. Okay, so I told you what these matrices U are, albeit fairly quickly. But now that I know them, I can go through the same process and write down the type binding Hamiltonian because I know the symmetries of these matrix tau and I know the symmetry of the spin matrices. And so then applying that, you can identify the symmetries of tau 0, tau x, and tau z and tau y. You find that they're an odd parity representation of D4H, they're B2U. You can use that symmetry and also know the symmetry of the x and y polymatrices. And then you can write down that the form of the type binding Hamiltonian in a way analogous to what we had before looks like this. So these two terms are the same. What changes is the spin orbit coupling. Now the spin orbit coupling, because this tau z is odd in parity, needs to be multiplied by odd parity functions. So it's the sine kx, sine ky. And then you can show that indeed this is an invariant. So you have polymatrix sigma x times sine kx, sigma z times sine ky. This looks a little bit like a Rashba spin orbit coupling, which we know breaks inversion symmetry. But now it's multiplied by this tau z operator. And this tau z operator is also odd in inversion. And in the context of cerium, rhodium 2, arsenic 2, we have ceriums on two different layers that are related by inversion. And so this tau z says that there's a Rashba spin orbit coupling in one layer. It's of opposite sign of the Rashba spin orbit coupling in the other layer. So that's how it applies there. But this is again for iron selenium. So the form of the spin orbit is slightly different for the cerium, rhodium 2, arsenic 2. Okay, so now I motivated iron selenium very early on by telling you that at the endpoint, there's two Fermi pockets that cross each other. So we need two bands. Now we're in a position to understand where those bands come from. Again, we can expand near the endpoint. And we can get our K dot P theory near the endpoint. So I've done the same thing as before. This term is slightly rewritten from this, and I've added a chemical potential. This term is exactly what comes from here. And then we can also do the same for spin orbit, but for spin orbit, okay, I guess I dropped a minus sign in this description. But nevertheless, we get something where sine kx becomes approximately kx and sine ky becomes approximately ky. And so that is our K dot P Hamiltonian near the endpoint. This is something that was also looked at in a lot of detail in a very nice paper by Chechevich and Vafek. If you look at that paper, you'll see the approach is very, very different than the approach we're using here. And they did this before Bilbao crystallographic server had all the representations written. So they chose actually even a different set of, they had different conventions for their group elements. They chose a different origin. So very much is different than Bilbao, but in the end, you get the same result. Okay. All right, so what I want to focus on now is, well, actually this Hamiltonian, I've told you that we get it for the iron selenium case. And so later I'll turn to iron selenium and talk about why that's relevant. But before I do that, I want to tell you some physically interesting features that come from this. And the first thing I want to do is just turn off spin orbit coupling. All right, so when I turn off spin orbit coupling, I only have this sort of non-trivial polymatrix term. And the one thing you notice is that if kx equals pi or ky equals pi, then this thing is 0. What does that mean? All around the Bruin zone edge, we have a 4-fold degeneracy if we add spin. If we don't add spin, we have a 2-fold degeneracy. Okay? So all around the Bruin zone edge, we have a degeneracy. And you might worry that that's a consequence of a particular choice of type binding. Maybe that's not a general feature, this degeneracy everywhere. But it turns out it is a general feature. And in fact, you can prove it's a general feature. And this is where the non-symmorphic symmetry shows up. So let's see what I have here. Yeah, OK. Yeah, I wanted to put something on the blackboard just so I can use it later. So I'm just reiterating what I just said, but making it explicit. So here's our 2D Bruin zone. And what I've said is all along the zone boundary, we have a 4-fold degeneracy, which comes from sublattice and spin. Okay? And what we're asking right now is this a general feature? Is this always true? Or is this just a consequence of my type binding model? All right, and in fact, what I'm telling you is it is always true. So in particular, I'm right now focusing on this particular side of the Bruin zone. And I know this particular side has a symmetry. It has a symmetry which is time reversal times mirror through this axis. So mirror through this axis takes a point k to minus k, but then time reversal flips that back. And so if I'm on that axis, we have that symmetry. So that's a local symmetry all along this line here. And so if I now look at what happens if I use the space group rules I told you about yesterday, well, since we have no spin, time reversal is just the complex conjugation operator. So that squares to 1. So I'm going to square this particular symmetry. But then if I square mx, you can convince yourself using those rules that that's a pure translation of 1 unit along the x direction. Okay, so that's 1 unit along the x direction. But now what we're doing is we're looking at momentum states that sit along this line. So kx is pi everywhere along this line. And so if I look at what this translation is represented by along this k vector, you can see it's represented by -1 because kx is pi. So now what does this mean? Well, here, this is an anti-unitary operator. This anti-unitary operator along this line squares to -1. We have an anti-unitary operator that squares to -1. We must have a Kramer's degeneracy. And so this is a Kramer's degeneracy that doesn't come from spin, but rather comes from sublattice. So this degeneracy here without spin orbit coupling is degeneracy from Kramer's degeneracy. Yeah?
If iron and selenium are inequivalent, which probably are, why don't I have tau z without any spin orbits?
Yeah, okay. So you're asking here in the form of this type binding why tau z doesn't appear without spin orbit. Yeah, so the reason is quite simply that tau z is an odd parity matrix in this case. And because it's odd parity, you can show that the constraint of inversion symmetry doesn't allow it to appear. In essence, it needs to commute with tau x, loosely speaking, and then, okay, it's not a great explanation, but it comes from that. And maybe we can sit down and work it through more carefully. Yeah, so the answer is imply inversion like the rules I showed you before, and you can rule out that tau z is allowed to appear. But the details of which we can sit down and work through.
Does inversion converts iron into selenium?
No, it interchanges the two iron sites. So here selenium is not at all, selenium is hidden, but it's not there.
Oh, tau z is not between iron, tau
Tau z is between iron sites, yeah, it's between iron sites, yes.
between irons.
Yeah.
Oh,
Yeah, I know this is maybe a little bit fast, but I want to get to applications, yeah.
It's purely iron.
Purely iron and x squared minus y squared orbitals on two iron sites.
But the non-symmetric nature comes from this arsenic, selenium part, right?
Yeah.
It's up, down, right?
Yeah, yeah.
So it is there.
It is there. So this is derived for a non-symmorphic group. So it is buried in here. But you're right. If we took the selenium away, this would be a simple square lattice like we had before.
Right. And this degeneracy is coming from the non-symmetric nature
Yeah,
theory, right?
That's exactly what that's
Right,
saying.
so
Yeah,
Right. If I don't ignore this part, I should not have this degeneracy.
that's right. So it does come from the seleniums, but somehow you have effective orbitals to find that know something about the presence of the seleniums, and that's the form of the tight binding that comes out from that.
Give two different iron because they have a different selenium in that.
Exactly. Yeah, you get two inequivalent iron because like you said, the selenium environment is different for the two. Yeah, the up down is different for one versus the other. Okay. Okay, so this fourfold degeneracy is generic. And so yes, so now I want to talk a little bit about that. And before I do that, I'm going to say that this kind of degeneracy, again, it shows up in many, many materials that are superconducting, not just in the iron selenium case. So I mentioned the cerium rhodium 2 arsenic 2. It also shows up in uranium platinum 3. And that's important because I mentioned this violation of Blount's theorem, uranium platinum 3. Exactly on this plane, you also get a similar degeneracy occurring. And so you get this fourfold degeneracy. And so it does play an important role in many superconductors. And so that's why I chose to focus on this particular degeneracy in here. Okay. Let's see if this works again. All right, so now I want to go back to the blackboard and talk about, oh yeah, one other thing I want to add here is, okay, we can add spin orbit to this, and we can ask what happens to this fourfold degeneracy when we add spin orbit. It lifts it in most places, except at all the trim points. Because at all these trim points, we have sine kx or sine ky. Kx and ky are either 0 or pi at these trim points. And so the spin orbit says that we have all these Dirac points, because there's a fourfold degeneracy here, which is now at a point at all these trim points. So this is with spin orbit. So fourfold degeneracy everywhere along the zone boundary without spin orbit. If we add spin orbit, we lift all that degeneracy except at all these trim points. And you can just look at the form of the Hamiltonian and convince yourself that's right. All right. Okay, so the first thing I want to talk about is just what can we say about superconducting orders now in the presence of this normal state Hamiltonian. And here I can't be exhaustive, but I'm going to show you a couple results. Okay. So I've told you what HN is. Yeah.
Before cutting, is there some topological charge or invariant associated to this degeneracy in the
Around the Dirac points.
not around the Dirac, but without spin orbit, like.
That's a good question. I don't know of one off the top of my head. Yeah, maybe somebody does, but I don't know. Yeah,
Before you go to superconductivity, can you go back to fermiology?
yeah,
And the question is, particularly, you started by saying that there are two Fermi surfaces and they cross.
Yes.
In the presence of spin orbit, I guess crossing will be lifted.
yeah. Spin orbit lifts that crossing. Those crossing points are exactly on the zone boundary in iron selenium. Right. And so we have that fourfold degeneracy on the zone boundary with spin orbit, and it's lifted by spin orbit. And I was going to tell you the story of why this gap function has no notes when you expect notes, but it looks like I won't have the time to get through that in detail. Maybe I can say it very quickly, but it has to do with the fact that we have a pair of Fermi surfaces around the M point. Maybe I'll quickly sketch that. So this is what Andrey was referring to. These are the Fermi surfaces of iron selenium. The crossing points sit on the Bruin zone boundary. So without spin orbit, those crossing points are fourfold degenerate. And so you're allowed to have, without spin orbit, you have a band crossing here. And it turns out when there is a fourfold degeneracy without spin orbit, you basically have a problem of two uncoupled bands. And then the superconducting order is plus on one band, minus on the other band, but it doesn't care about this crossing point at all. This crossing point at all. And so what you get is just a fully gapped system because they're uncoupled. But the second you turn on spin orbit, you will start to couple this, you will split the bands, and it turns out the nodes that you thought should be there reappear. And I was going to give some more about that story later, but I think, well, maybe we get there, maybe we don't. So, okay. Okay, so I can't do an exhaustive analysis of delta, but I can show you some relevant deltas, some relevant superconducting orders that appear in real materials or that are often discussed in real materials. And so just so that you get a flavor, our BDG Hamiltonian was right. That was the form we were using, and that's what we're using throughout this. I've talked about this part, now I'm talking about that part, okay? And so our first simple gap functions. So this is just the usual single band psi of k extended to the two band system. And so I just multiply it by a tau zero Pauli matrix. And so this is just usual spin singlet. And we can also do usual spin triplet. I forgot the K here. This is usual. And so nothing really new comes from this, but at least we see how to go to the larger space, including that. All right, now let's talk about some of the more interesting cases. So here, so this is the case that I think is relevant for monolayer iron selenium. So again, if we extend near Kx and Ky as pi, both these numbers become 1. And so this is a constant gap in iron selenium, but it's a little bit inconvenient. Our normal state Hamiltonian has a term proportional to tau x. And so if we go from the way we've written it to our band basics, then tau x goes to tau z. And what this means then on the two bands, that this has opposite gap on the two bands. So this is the state I was mentioning before that I drew over there. So this is the iron selenium case, but now we've extended the momentum dependence, not just near the endpoint, but through the entire Bruin zone. And the only thing to point out is that same rule associated with reciprocal lattice transformations apply to this order parameter because we want the BDG Hamiltonian to have that same property. And you can explicitly derive that, but I haven't derived it here. So I'm telling you that's a property. Yeah.
Sorry, forbidden question. What's the meaning of superconducting gap away from the Fermi surface?
Oh, okay. I mean, yeah, so.
Forbidden question.
Yeah, I mean, this is, so I'm imagining that we have a Fermi surface and I can move it away from the endpoint, maybe put it near the gamma point, and then you can see things behave nicely from this. But yeah, you're right. But I'm just writing the form down so you can put it in. I mean, in the end, you need to, yeah, I agree with you. You need to restrict it somehow near the Fermi surface. But I'm just showing you the forms. So this is a dxy gap. And notice, if I work near the gamma point where both kx and ky is 0, then sure enough, when I expand this, I get kx times ky. But near the m point, this becomes 1 and this becomes 1, and then all the d-wave nature is buried in this tx. But again, if we want to understand this tx, we have to understand this tx in terms of the representations of the little group at m, and this tau x does belong to this dxy symmetry. So that's where you can see everything being consistent in that sense. Okay. Okay, so this is monolayer FESE. And then I can show you another gap function here. I can write down delta tau z I sigma y. Okay. And this gap function, well, not exactly this gap function, but something like this gap function matters for cerium, rhodium 2, arsenic 2. And so here, there's something very interesting about this gap. So it's tau z, so it doesn't have these 1/2 showing up, but it's uniform all across the entire Bruin zone. And in particular, this gap does not satisfy the property, yeah, that's everything, that delta G over 2 is 0. And I told you odd parity gap functions satisfy this property. This is odd parity because, as I told you, this tau z in our formalism is B2U symmetry. So this is an odd parity gap. The reason we get around this is actually tied exactly to the fact that in this band structure, these half reciprocal lattice points develop a fourfold degeneracy. So at all these points, we have a fourfold degeneracy. And the earlier picture was for a single band theory where we only had a twofold degeneracy. This other 2 degrees of freedom allow us a way around the Pauli exclusion principle that enforce that. So this is an example of where you use the multiband or the multi-degree of freedom nature to write down gap functions that are non-zero, again, when you expect them to be 0. Okay. Okay, I had one more example, but it's a little bit more obscure, so I'm going to skip that one. So in cerium, rhodium 2, arsenic 2, the physics is you start out in 0 field with a normal spin singlet order parameter, but then you apply a field along the c-axis, so it's a tetragonal material, and you find there's a first order transition into what is believed to be an odd parity state. And that's exactly this odd parity state, except on the layer basis, it has a gap of +1 on one layer, -1 on the other layer, and that's an odd parity state. So, and I won't go into any more details of that. The other example I was going to show you, well, maybe I'll quickly show it. It's a little bit more obscure, not as helpful here, but it has been discussed. Okay, let's write it this way. Yeah, I guess it is useful. All right, so now I'm considering an order parameter with the tau y component, so I need to satisfy the reciprocal lattice rule. And now I'm writing down a spin triplet gap function, but it's different than the single band case because the spin triplet gap function is multiplied by this function that's even parity. And the reason we can do that is because this tau y matrix satisfies our Pauli anti-commutation relationship, because this is an anti-symmetric matrix. Under interchange of the 2 sites, we pick up a minus sign. And so this thing is allowed gap function. So this isn't discussed in any materials I've talked about here. It's perhaps relevant in uranium ditelluride. It's not clear, but people have talked about such orbital singlet spin triplet states in the context of strontium rutheniate. Also in the context of twisted bilayer graphene, such states have shown up. So it's worthwhile pointing out, but then in those other examples I mentioned, the nature of this tau Y matrix is actually sometimes a little different, but at least you can see where it shows up and how it's different than single band case. Okay, so that's some gap functions. And now I'm going to tell you another useful result. Okay. So we define all these gaps. Yep.
Can you have orbital singlet, spin singlet, hot parity superconductor,
An orbital singlet.
spin singlet, and hot
Yes,
parity?
you can.
Yeah, you can. Yeah, you can. Yeah, and I mean, these have been classified in places, but I haven't seen any materials people give a serious case for that state to exist. And in the other cases, there is some plausibility argument to say these exist in some places. But okay, I haven't read everything, so maybe it does exist somewhere. Okay, so the way we've written it now, we've used some real space basis in which to characterize everything. And this matrix HN is not diagonal, right? It's not in a band basis. And one thing we often want to do, especially in the context of superconductivity, is go to a band basis. And then we have to ask the question, how much of delta acts within a band and how much of delta acts between bands? All right, and there's a very simple condition that lets you understand that. And that's this idea of superconducting fitness. And so here, I imagine I write my gap function as some delta tilde times my I sigma y, or my unitary part of the time reversal operator. And then I can tell you if the gap is purely intraband or purely interband by just taking commutators and anti-commutators. So if it's purely intraband, and purely interband is called fit, because all the gap shows up in the intraband part. There's no interband mixing. The condition is simply that delta tilde and HN commute. So if those operators commute, the gap is purely intraband. If they anti-commute, this is purely interband. And what that means is if it's purely interband, there's actually no BCS log to stabilize the state. The only pairing is between two different bands, and then you don't have the degeneracy between a state at 1K, one band at momentum K, and another band at momentum minus K. Those are no longer degenerate. So there is no BCS instability here, and here there's a BCS instability. So this is fit, this is unfit, you can say. In practice, you get a mixture. So part of the gap commutes with HN, part of it anti-commutes with HN, and so you always have this mixture of fit portions and unfit portions. But all that means is that the TC you might naively have expected will be decreased as and only restricted to the portion of the gap that somehow commutes with HN. Okay. Yeah, so I'm going to use fitness in a second. Okay. It looks like I have time really just to address this question about Blount's theorem and why it's violated in some cases. And so let me do that. All right, so let me just remind you what we said about Blount's theorem. I think that's the last thing I'll do here. All right, so Blount's theorem was simply a statement that first we saw in this class C2, there should be no gaps. But then we had to add mirror symmetry to allow us to get a gap. And in a mirror symmetry, we found that two of these functions can be odd under mirror and one can be even. But because two of these functions can be odd under mirror, they can vanish on a mirror plane. And then suddenly we have a condition that allows us to have line notes. But the key physics was dx and dy had to be had to be odd and dz had to be even. If we want to violate Blount's theorem using the same argumentation, we need all dx, dy, and dz to have the same mirror symmetry, either even or odd, okay? Then we can, in principle, get a line node. Line node in 3D is the same as a point node in 2D. So what I discuss here will be a point node in 2D, okay? So, but what I want to consider now is Fermi surface around the M points. And I want to intersect on the Brillouin zone boundary again. And what I'm going to argue is here, we can have this violation of Blount's theorem. And so to see how that happens, I'm going to first choose a gap function that will eventually violate Blount's theorem. So this is just a conventional spin triplet state. And then, okay, I'll have an I sigma y here. Okay. And then on this, so I'm going to focus on this point. So delta at this point, let's call this point ky tilde, kx is 0. So delta at ky tilde is just tau 0 sigma y sine ky tilde I sigma y. All right, so if I have no spin orbit coupling, I have two bands, everything is degenerate here, they're uncoupled, so I'm going to have a gap, right? This is non-zero, it's going to give me a gap at this point. So without SOC, and this is consistent with Blount's theorem, but Blount's theorem actually applies to with SOC. So now what I'm going to do is I'm going to add spin orbit coupling. I've chosen a point on the Brillouin zone boundary, so the only term that matters is the spin orbit term. So Hn at this point ky tilde will have some epsilon 0 term, but then it has this spin orbit term. Has this spin orbit term. So that's the spin orbit. And now I'm going to ask, if I turn on the spin orbit, do I still have a gap there or not? And what I'm going to use to tell me that is exactly this superconducting fitness. So I'm going to ask, does my normal state Hamiltonian commute with delta? That tells me I have a gap. Or does it anti-commute with delta? That tells me that this is purely interband pairing and I have no gap. And you can see I've done things correctly. These are going to anti-commute. Right? So here, Hn comma delta. So this implies we have purely interband pairing. And hence, if we go to the single band limit, there's going to be no gap here. This is a point node in 2D, which is equivalent to a line node in 3D. And hence, we have a violation of Blount's theorem. And you can kind of see where this is going to come from. I've already hinted at the answer over there, but this will be the last thing I do. So where does this come from? Well, the key is first, we know that mirror symmetry is important here. And so I won't go through the details, but you get some idea of where this comes from. I can derive the representation of the X mirror near this point, okay, near this K point. And it is exactly this, okay? And so now I can look at the form of the Hamiltonian there, and you can see that Hn is proportional exactly to this tau z sigma x. So the normal state Hamiltonian is proportional to this mirror operator. What does that mean? Well, when I diagonalize the normal state Hamiltonian, I'm going to find out that it's going to split into basically two sets of states, but the two states that are degenerate will have the same eigenvalue of the mirror operator. So basically, they'll have the same mirror symmetry. And that's loosely speaking. So this implies, yeah, so let me write this state down. So the key point of this observation is that degenerate eigenstates have the same mirror eigenvalue. All right. Those mirror eigenvalues are plus or minus I. And that's because we have spin present. And you may realize that if we have spin present and we do a twofold rotation, a 2 pi rotation, we have to pick up a phase factor of -1. If I square mirror, that's equivalent to a 2 pi rotation. And so when we square that, it has to be -1. We look at the eigenvalues of -1, those are plus or minus I. So that's why this plus or minus I comes up. But let's not worry. Let's choose a pair of states. Let's say mx plus minus. So these are our 2 degenerate band states. And these are going to have the same eigenvalue under mirror. Okay? So that's what we just argued. These are the same operator, basically. So they're going to have the same eigenstates. And so we can do this. And now we can say, let's make Pauli matrices from this band basis. So now let me make Pauli matrices where here I comma j are within a single band, so they're plus or minus. Right? And Pauli matrices are just linear combinations of these for different plus minuses, right? All right. And so what I'm going to do now is apply a mirror symmetry to this and ask what happens. Well, they all share the same mirror eigenvalue. So this is going to pick up a factor of I, but this is the Hermitian conjugate of that. So it's going to pick up a factor of minus I. And so this thing is unchanged. What does this mean? It means that all the Pauli matrices are even parity under this mirror symmetry. And so the upshot is that we get exactly this condition. We have the possibility that all dx, dy, and dz are allowed to vanish. And the physics of it is because of the multiband nature, the nature of pseudospin on this Brillouin zone boundary is different than what happens with usual spin. And that allows us to violate Blount's theorem. And if you look in detail, it turns out every example of violation of Blount's theorem comes from this kind of physics. All right, I'll stop there.
Andrey,
What is the last?
anyone else?
Okay, let me start, maybe I will initiate the discussion. About iron selenium.
Yeah.
You phrase your consideration as let's do it without spin orbit and let's add spin orbit. Now let me do it slightly different. Let me say spin orbit is there. I don't care how it obtained, it is there.
Yeah.
There are two Fermi surfaces and they're split.
Mm-hmm.
What about what's called other S? Other S plus minus. Plus on one, minus on the other. Where it is in this classification?
It's hard to do. To be honest, I have a hard time. So I've thought about that state and I have a hard time writing it down.
But it
is there. And so, yeah, you have to think about, so it's clearly not written in terms like this. And so you have to look at what spin orbit couples. So I don't know how to write it down in a real space basis. So my instinct is that's probably not a realistic state in these material, in this particular case. I know it comes from, you can model it. Maybe you have a different opinion, but
No, I mean, but suppose the spin orbit is large.
yeah.
Former surfaces are split essentially.
Yeah.
And that's a viable option.
It is a viable option. I guess we can figure it out, but I have to sit down and think about it. But spin orbit has this tau z operator, so maybe it means that we can figure out a way to do it. But yeah, good question.
Yeah, okay.
Is there a way to understand what this commutation, anti-commutation?
Yeah, I just told you the answer. Is there a simple way? Okay, so this was derived by Aline Ramirez, and I helped in some sense. But it is, you have to solve the self-consistent gap equation, and then you have to write it in a way where you take care of the Green's functions. You write the Green's functions in a band basis, so your projector operators included, and then you can see how this algebra comes out. But it's not, I mean, I can tell you a little bit more, but it's going to take some pedaling to go back to Nambu space, because I haven't got any Nambu space here, right? These are just corners of the matrix, but I can tell you a little bit more about where it comes from in that sense. But the point is, anti-commuting matrices tend to gap, and commuting matrices tend not to gap. And so here, if we go to Nambu space, this commutator becomes an anti-commutator, and so it tends to gap, and that's what we want. So maybe that gives you an idea.
Can you tell us a little bit more about this fit versus unfit? I don't quite get that. Like, why are you calling it fit?
So fit because intraband gives us the BCS instability. That's the usual instability we write down. So you want as much of this gap to project onto the intraband as possible. So a gap that is fully fit in that sense is going to have the highest TC. If we go to this limit where it anti-commutes, that gap is completely unfit and has no BCS instability. So that's why we call it. So in practice, you're going to get some combination, but this commutator part of it, whatever it is going, or yeah, the other way around, sorry. But we want as much of the gap to satisfy this as possible. So
in principle, your system develop both intraband and interband pairing
yes,
at different temperatures.
yes. And then the full gap function has to distribute itself somehow between intra and interband. And so if it chooses to be fully intraband, then that's going to have the highest BCST given some interaction. If it chooses to be fully interband, that will have no TC in the BCS limit.
Has some TC, right?
No, okay, it has no weak coupling TC.
Like some finite interaction. No?
Yeah, it can be turned on by a finite interaction, but it doesn't have an infinitesimal U interaction. Yeah.
And do you, like, for example, for this iron selenium, you have this pair hopping interaction which gives superconductivity in the like here, what kind of interaction gives me this interband
This?
pairing? Yeah.
Yeah, so the interaction that can do that is if you imagine spin fluctuations where the two moments are like this on the two iron sites. So that if you treat that within a simple spin fluctuation mechanism, you'll get this state.
Yeah, go ahead. Okay.
In a purely interband pairing superconductor, is there a supercurrent protected by the exponential cost of generating vortices? Or I don't know if that's...
Yes. So if you have an interband,
Forgot.
oh yeah,
Repeat the question.
yeah, that's right. So the question was if we have a purely interband superconductor, so no BCS applies, and we get superconducting in a superconducting instability, so you can have that for some finite interaction, then is the state still going to carry a stable supercurrent? Basically what you're asking. And the answer is yes, because that supercurrent is a phenomenological consequence, and we can still write down a Ginzburg-Landau theory for this order parameter, and everything from that Ginzburg-Landau theory still applies. So you're still breaking, U1 gauge invariance exactly the same way as before. So there's no reason to not expect it's a superconductor. The only thing you might ask about is perhaps the phase coherence becomes, phase fluctuations become very strong. That may suppress TC, but everything should be okay.
So interband pairing, is it like FFLO thing? Finite momentum, FFLO?
Yeah, so yes. So if you have a purely interband pairing state, a natural question to ask is, do you get an FFLO state? And that's exactly what happens in FFLO. What happens is you take your spin singlet Cooper pairs, you apply a field, and then when you apply a field, your usual singlet interaction becomes purely interband, and then you drive the FFLO state. So you can drive FFLO that way.
Is there something qualitatively different that would this Hermitian inclusion of tau y matrix do if, for example, as you mentioned and didn't discuss, have time reversal and maybe some mirror symmetry instead of inversion? which, so is there something qualitatively different of having tau y?
Of having, so the question, if I got you right, is I pointed out this possibility of the gap in the tau y case, so which is, yeah, in this particular problem was some odd parity spin triplet state. And you're asking, are there qualitative differences coming from having such a tau y state? So at first pass, if you go to the intraband limit, so if you're in a place where only single bands matter, then in practice, nothing is really going to be different from the single band theory. I mean, maybe you'll get this change of the symmetry of these matrices and things like that, but nothing's really going to be different. But when you get to the situation when the two bands become near degenerate, then you can start asking about this legitimately. And in principle, there can be differences, but they haven't been well explored.
So I think Andrey, you have a question?
Yeah, very it's conceptual question, genuinely, about this concept of fitness.
Yes.
Does it have any predictive power, or the way how at least you presented it, the gap is already known, and you just check whether the gap commutes or anti-commutes Hamiltonian. But in some sense, if the gap is known, that's it. You don't need anything else.
Yeah, I mean, so it is useful in that sense, but it does help in developing a theory because you can say, suppose I want this gap for some reason. So if the gap is known, then you're stuck with the numbers that come out. It is predictive in the sense that you can say, I know the interaction, I know the amount that is fit, and I can from that get TC, and that'll be less than the fully fit TC. So you can say TC will be suppressed in the exponential by this fitness factor. So there's some predictive power, but it's more useful, say, suppose you have a spin triplet superconductor, and you have 3 spin triplet states that are all degenerate. Then you can feed this into the normal state Hamiltonian, and it'll tell you right away which one wins. So if you have some degenerate pairing channels, then it's very useful.
Any other questions? Okay, if not, let's thank anyone. Back here at 11 to the next lecture.
Well, you could do comments on
You only have to stay see the reason. Then you have to.
Yes.
Consider 1 over 1 minus.
Oh, yeah, don't worry. Yeah, wait.
This gives you 4.
I would consider a particular as you'll see that on the left hand side, you have something diverging. And on the right hand side, you have something combining. Therefore, I have
And I have my group in terms of like descent and it gives me exponential decay like this.
okay, so all sides over G. You see why there So yeah, so I'm saying that here's a proof. So you're saying that there are counterexamples to proof. There should feed in that counterexample to your calculation.
Then it changes
E here is minus two domain and the is the
So I just like consider the negative sign, but you also get a negative sign. Yeah, so it gets cancelled. Right, that's why I'm talking about. So you think like also like dependent here, you need to spend like your. But even in that case, I think you come for some reason, right, exactly. I think he discussed like some thematic factors. Why does calculations? No, I think I'm missing.
Out of a thematic phase.
Right, I need to like.
Yes,
we can call it.
No longer orthogonal due to the polarization problem.
Yes,
Superposition can happen daily. Yes, plus I alpha d.
Using some of the formulas.
Account for the one, the first subletters is 0, 0, and then the one dollar that in fact the kind of
So it's because they're yes. So that will be some new like so one. They'll change this.
Yeah. Like one part then you're like second extra one. So then you give us one
I think almost one
You can always just raise the energy, right, temperature, use some energy.
Yeah.
That's.
Okay, so last lecture I was trying to argue that under certain conditions, especially at low density, probably Agterberg is not your friend in a sense that, well, lambda is still much smaller than 1. If you do BCS type analysis, your transition temperature is exponentially small. And suddenly you see you already have to give up and consider another limit. Where instead of considering Fermi liquid behavior and instability close to the Fermi surface, you have to discuss properties of the polar. Unfortunately, I have no idea about a single material where this applies. If you ask me, do we know at least one material? Well, then we definitely have bipolar on superconductivity. And my answer is, I am not aware. People were suspecting, people were predicting, including high TCs, maybe dozens of papers written about this. But I would say there is no convincing evidence. Still, the mechanism was discussed. So let me kind of more or less finish the job by establishing the framework, what you have to do. Because it goes back maybe several decades and it was very popular with Alexandrov and Mott. Okay, the same Mott. Pushing the mechanism forward. But there is one problem. So whenever it comes to the bipolar mechanism of superconductivity, you cannot be semi-phenomenological. Everything actually boils down to, okay, well, what are the numbers? And I'll try to convince you that, okay, without the numbers, you can talk about the possibility of having high TC with bipolarons. But once you start plugging in the numbers, the picture may be totally opposite. And then probably you have to explore other models which people never did before. So I'll try to say, okay, well, but in this business, you can be very, very precise. So unlike in BCS, where any small mistake in the exponent will immediately change TC by orders of magnitude, this mechanism has other very nice properties. Ultimately, you have to go and solve properties of bipolar now. But this is a two-body problem, which means you can do much better job in understanding properties of two particles. I'll just try to explain, okay, how this is done, and you can do extremely good job this way. But then once you have bosons, my argument will be your job is more or less done. So let me explain. Yeah. Okay, this is not reacting. This one does, okay. So I'll start with something which is kind of trivial. To go superfluid, if they're charged superconducting, bosons don't need a mechanism. Unlike with fermions, we say, okay, you need certain type of attraction, or you need repulsion with certain properties. So I have to take care of polarization and consider Confidel oscillations. I have to do something about the mechanism, and to end up with TC, which is strongly dependent on interactions and the way how you treat them. With bosons, it's different. With bosons, more or less, they will condense all by themselves in 3D. I'll go to 2D a little bit later. So in 3D, you take ideal Boser gas, it will condense. Yes, it's unstable for other reasons. You need kind of sound dispersion relation at low momenta to stabilize supercurrents. But at least TC can be predicted from the ideal Boser gas expression. And it's a little bit kind of outrageous how well it works, because if I take helium-4 is a very strongly correlated liquid. Just a little bit, because in terms of condensed matter parameters, a pressure of 25 bar is almost nothing. But you do 25 bar, 26 bar, and helium crystallizes. So it's a very strongly correlated liquid, almost on the edge of making a crystal. And still, TC in helium-4 is only 70% of the ideal gas expression. So if I take helium density, bare mass, put here 3.31, I'm not that bad. I would say in terms of conventional superconductors, generically having the security of 30% in predicting TC in any material out of the blue, this would be outrageously good. But that's what happens in helium. You can say, okay, well, maybe this is kind of a particular case in nature. Unfortunately, we don't have many bosonic liquids as experimental systems, but that's what we have. Also, sometimes there is a very popular discussion of, I know, 4 fermions pairing, but they say, okay, come on, helium is a 6 fermion pairing. Well, because you have, I know, 2 protons, 2 neutrons, 2 neutrons, 2 protons, and 2 electrons, 6. Well, count quarks, it will be 14. I'm saying that, well, just still kind of pay attention that whenever almost everything about even high energy physics and definitely about condensed matter physics, bosons show up only as bound states of fermions. We don't have bosons otherwise. Okay, not discussing any virtual states like Higgs. Actually, sorry, I have to say it. Higgs is not a particle. Okay, so there is no particle because there is a field, and we know that there are amplitude oscillations of the field, and those amplitude oscillations give you some resonances. It's a signature that we have a condensate of a certain type, but it's not a particle in this sense. Yeah, it's a collective excitation, but what are the prime degrees of freedom? That's not the Higgs. Okay. But again, this, yeah.
But above the ultra-weak symmetry breaking scale.
Sorry?
But above the ultra-weak symmetry breaking scale,
Yeah.
you have an extra
Sure.
Gabor particle.
No, I don't know what the particles are. I have never seen them. I only know there is a condensate. That the condensate is there, I know from the collective mode.
But you are within, you are in the low energy regime. If you go to high.
Yeah.
So sport.
Please go and see what happens there. So nobody knows yet.
What many people in Collider?
No, I know. Just I'm slightly joking in the sense that yeah, that's what we have. Actually, it doesn't deserve the name in my point of view. Yeah, there is a massive goldstone.
Oh, that's a low energy.
No. Massive goldstone is precisely
Massive
massive goldstone. That's what was discovered at CERN.
Oh, yeah.
That's called massive goldstone.
Okay. Yeah.
That's the name.
Okay.
Because goldstone has a paper. Everybody says, oh, it's about phase mode. Gapless excitations. No. Goldstone paper is about two excitations. One of them is related to symmetry breaking and supposed to be gapless. If the system is not charged, then there is no local gauge invariance. But the other one is amplitude mode.
Yeah, the real mode.
It's the amplitude mode. That's the massive Goldstone.
Or you call it.
And there is no other, not me. Goldstone's paper introduces this mode and discusses its properties. It's a massive Goldstone.
Okay, that's an unconventional name. I would say.
No, this is conventional name when Goldstone did it. And then it changed over time. I don't want to go to this one because some people wanted Nobel Prize too early and they decided to put the right person under the carpet so he doesn't show up anywhere. Okay, but otherwise we have fermions. But I have to pay attention that even if we talk about bosons, we have to pay kind of some attention to how strong is the bound energy. Because if we bare electrons or any type of fermions, it's important what is the binding energy. And more or less when we start talking about point bosons, well, more or less we assume that if the binding energy is much bigger than any other energy scale you are interested in the problem, for example, DC, then I don't even have to think about bosons as composites. Because they have internal structure, but this internal structure cannot be excited, so treat it as just one. And that's what we do with helium. Essentially, all simulations of helium are done assuming helium is a boson. You can predict TC numerically, for example, with accuracy better than 1%. You can go and measure and you'll have exactly the same TC. Yeah, this is just the estimate, which is 30%, but you can, numerically, you can finish the job up to sub%. This is just for the picture. And then I say, okay, well, if I want to discuss some interaction effects for interacting bosons, we actually have a perfect tool to answer almost any question about bosons. I will just say, as long as the dispersion relation has a minimum at k = 0. Because I know there is other considerations which say, okay, well, sometimes you have a more add dispersion relation with spin orbit coupling. This is completely killing the technique which I am trying to explain. Yes, you have still interacting bosons, everything is everything is the same. But the moment the kinetic energy has a minimum, for example, on a circle or a sphere, this is a totally different physics. Just for you, if you don't know it, just read some of the papers and you'll discover that if the minimum is unique, say k = 0, bosons will condense. The moment the minimum is not at 0, but a degenerate manifold like a line, you think, oh, how do they condense? At 2 points on the line, equally everywhere on the line? And the answer is no, they just go and become fermions, almost fermions. If you don't know this, this is a separate discussion. Okay, I'm assuming that bosons have a minimum at k = 0, so there is more or less conventional setup.
This Q depends on the relative ratio between the Q at which they condense and the size of the Fermi surface, or it's independent?
If the minimum is on this, say, on the line, like what's called Moyet dispersion relation, weak interactions between the bosons will already kill their statistics. You will not even know just, okay, well, that you have bosons. In the low energy subspace, there will be no bosonic degrees of freedom. You will have Fermi surface.
So yesterday when you were saying that because of this phonon and electron interaction, phonon branch becomes soft. And
no, it's totally different. No, I'm not talking about this.
But there also, when that happens, you have minima at some other k, right? Then also like.
But those are phonons. They don't have U1 symmetry. Their number is not conserved. Forget about this. They're not going to condense.
I see.
In this sense.
Okay, right.
No. I'm talking through U1 when the number of particles is conserved. Yeah, so what's the technique? It's called path integral Monte Carlo, introduced by Separately and others many years ago. Simply slightly modified for the proper kind of efficiency. It says, okay, well, you can describe the partition function or the Green's function of the system by configurations. Like partition function is just particles trajectory in real space with proper permutations on the periodic boundary conditions in the imaginary time. So those are configurations for Z, just like polymers in the D+1 dimensional space. You simulate their properties, you have the partition function of the system. You can open one of the line, but this will be the Green's function. You create a boson at one point and you delete the boson at another point. We give them the names, it doesn't matter. And then you just can perform Monte Carlo simulation by simply updating this configuration space. And as you do it, okay, well, those are kind of the typical updates. You can switch between the two subspaces. If you take partition function space, cut a little bit the line, you go to the Green's function subspace. Then you can do simulations in the Green's function space. This is what will give you permutations. But if I propagate n points in space and time, I'll just become ergodic and I can generate any trajectory I want. So this is literally like drawing and arranging, whatever you like. It's very efficient. You can do grand canonical ensemble. Automatically, you have a full Green's function in space and time. Of course, if I take 0 time, you'll get the density matrix. You can also study the condensate wave function, superfluid density, correlation functions, just whatever. Ask any question about interacting bosons. Path integral method will give you the answer. This is not kind of to introduce the technique or discuss it too much. This is just to convince you that we have a tool to give the answer for the interacting bosons with very high accuracy. So what do we learn? So let me start with the early examples when people were interested in kind of universal type of questions. What happens to the transition temperature in the Boson gas if you switch on interactions a little bit? Well, it turns out that, well, if you switch interactions on top of the ideal gas in 3D, the transition temperature actually goes up, which means repulsive interactions between the bosons, they're not hurting TC at the beginning. And actually for, I don't know, starting from very low density, when you have well characterization of this curve, it simply says, okay, TC will go up as NA to power 1/3 with some number C. For many years, people were fighting about this number C. Now we know this number. Well, yes, numerical data are more or less, not more or less, numerical data are consistent with this behavior. And then you can go to pretty high densities and look at the vertical scale. Yes, you do hard sphere gas, you do soft sphere gas. Soft sphere simply means, yes, bosons can approach each other easily, but there is some repulsion starting from a certain distance. Yeah, the whole scale is 0.99, 106. So it's really plus 6%, minus 1%. Then the curve will start going down, but that's when, for example, hard spheres are already almost touching each other. Just a little bit more and they will crystallize. Because this is already kind of going to a density 1/10 in terms of the radius of the sphere. So unless I go and try to crystallize the bosonic liquid, everywhere else, more or less, my transition temperature is barely different from the ideal gas expression by a few percent.
So this correction term is within Bogolyubov. Can you capture?
This is not Bogolyubov. You cannot compute this one.
Why not?
It's coming from proper kind of changing physics in the fluctuation region. There is no analytics whatsoever. You cannot do it. You have to do it numerically. That's why over the years, people had, say, 20 papers. One paper would say -2, then -1, -0.5, -0.25, and then positive, same number. And so ultimately, you have 20 numbers all over the scale, and somebody is probably close to the answer. And actually, the power was also changing from one author to the other. People predicted 2/3, 1/3, all over the place. It's not a mean-fieldish.
So this number is that from this
Even this power was questionable, but I would say it's not questionable. You have a good universal understanding, okay, why it has to be 1/3. But whether this is plus, minus, and what's its value, this was very controversial. Yeah.
Perturbation theory if parameter is small.
Yeah, it's coming from the fluctuation region, and you cannot just do it. Well, you start from the mean field. It's one. Let me explain. You start from the ideal gas. That's the Gaussian universality class. It's ideal gas, mean field, and everything. The moment you introduce fluctuations, interactions, this is generic U1 universality class. You change critical exponents, you change everything. So the entire change from ideal gas to generic U1, that's your fluctuation region. So you cannot do it analytically because everything is non-perturbative in this case because you are changing universality class of the model. If it's a good enough answer. That's why I'm saying, just trust me, 20 people have written 20 papers and the answers were all over the place. because you cannot control it, which means you do any different approximation, you have a different idea, you have a different answer. We submitted paper by some luck. We submitted it to the archive. Our paper was 4 pages long. Next day, they submitted a paper which was 20 pages long. We had the same answer. So for whatever reason, we would simply just scoop them, even though they were working on the problem much longer and much more precisely, much more detailed. So the answer was more or less pinned at this point. Yeah, so that's what behaves here. So yes, it's increase. You say, okay, why did it increase? Remember, there was a discussion, phase fluctuations, but ideal gas has also very large density fluctuations, because once you touch TC in ideal gas, you have divergent compressibility. Yeah.
Do you have any intuition for why the TC starts falling down first, soft instead of hard?
I'm trying to crystallize. Well, because they know about the space being already restricted earlier, because soft sphere means the following. It's in terms of the scattering length. But for soft sphere means for the same scattering length, the interaction radius is bigger. So they know earlier, and I excluded volume as actually cubed. So they know much earlier that, well, okay, they're already touching each other.
So soft is a bit more long range than hard.
Yeah, longer range by construction, yes, more or less. Yeah. For the hard sphere, I think A and the sphere radius is the same. So that's one. You say, okay. You have interacting both the gas like hard spheres, soft spheres. Don't even bother calculating TC, please. Write down 3.3. Just don't be more accurate than a few percent. You're not mistaken. This doesn't answer the other question. You say, okay, yeah, this is short range model. Of course, you have hard spheres, soft spheres, short range. What if you have Coulomb interactions? That's the relevant one for the bipolarons. So suppose you create electronic pairs, but if I'm talking about superconductor, they couple by Coulomb forces. This can be totally different picture in principle. So that's what we did, I know, more recently, just trying more or less to answer this question, because not answering the question, I'm not responsible for what to expect for TC in the mechanism. If you form bipolarons and they're charged particles, how do you compute TC now? Yes, I have charged bosons, effectively. But how do I compute TC for charged bosons? So that's why we decided, okay, to look at this problem kind of more carefully to see, okay, how much TC will change relative to the ideal gas behavior if we introduce Coulomb interactions, and the answer is don't even bother. Sorry, kind of, it's a lot of work, especially because long-range interactions are very expensive numerically ultimately, but the outcome is forget about our work. Just write down ideal gas expression again, because this is what we have in continuum. Just take continuous Bose gas and add Coulomb interactions for different values of RS. Okay, RS. This was the question. What is RS? You take interparticle distance and express it in terms of the Bohr radius. What is large RS? Large RS simply means that, okay, interparticle distance expressed in terms of Bohr radius is large. Well, which means Bohr radius is much smaller than interparticle distance. It's kind of when charges are very well separated, that's when the kinetic potential energy will start dominating. Because kinetic energy drops as 1 over r squared, Coulomb interactions will drop as 1 over r. And if I go to a more and more dilute gas in terms of the Coulomb interactions, this is stronger and stronger correlated. So that's why large RS, it's a very dilute case, but that's precisely when correlations are much stronger. Well, we did calculations all the way from, I know, small RS, 1, 2, 3. Again, at the level of 1, 2, 3, you barely see any difference from the ideal gas. For RS 1, 2, 3, 4, 5, almost nothing. That's where we are sitting. This is already like RS equals 5, then you barely see deviations from the ideal gas. Then it will start dropping, and after RS equals 50, you start thinking about the Wigner crystal physics. Because that's when your liquid is already trying to crystallize. Okay, TC will drop by 6%. Next, you say, okay, well, maybe lattice effects are damaging. So we did the same kind of Coulomb gas. So this is when Hubbard U and Coulomb interactions are comparable to hopping. This is blue. You have your 5%. Well, or you have green, which is much stronger when Coulomb interactions are outrageously strong and Hubbard U is 8. And Coulomb interaction is counting from the nearest neighbor side. On the nearest neighbor side, Coulomb interaction is also 8. And then it just drops as 1 OR. Okay, that's the change. Yeah, it's somewhat stronger, but again, with 10% accuracy, you will not be mistaken if you claim an ideal gas. Here I'm simply express the same data in terms of density. So that's why kind of ideal gas continuum, all of this part is more or less compressed to those kind of points. Well, okay, well, this is in terms of density on the lattice. Okay, just not that important. How you express the data. Yep.
So if this is the case where we are adding Coulomb interaction, what were the interactions that you showed in the previous slide? You said that with interaction, the TC was first increasing and then decreasing.
Yeah, well, here also TC goes down when Coulomb interactions are getting stronger, stronger, and stronger, because here I will get a Wigner crystal.
But what were the interactions in the previous slide? So there was no Coulomb interaction there, right?
No Coulomb interaction on previous slide. This was soft and hard spheres.
Okay.
Hard spheres simply said, okay, two bosons cannot come closer than a certain distance A. Hard spheres.
Okay.
Or two bosons can come closer, but then you have potential energy of repulsion if they are closer than a certain radius. Everything was expressed in terms of scattering length.
And the TC here is the TC to form the BEC.
TC to go superfluid, yes. It's a three-dimensional system, so you have true long-range order. Yeah, that's true TC. So that's what we more or less learn and can stop in 3D. If you have interacting bosons, no matter how, lattice, continuum, Coulomb, short range, long range, you don't go far away from the ideal gas behavior unless you want to crystallize or create some other phase competing. For example, on the lattice, in cold atoms, you can also kind of create bosons on the lattice, make interactions stronger, stronger, and stronger. For three-dimensional bosons, if you go to interactions on a scale of, I think, 30 hopping, the system will try to create Mott insulator when the density is 1. And then your answer for TC will be roughly ideal gas. But once you are 3 or 4% from the critical point between superfluid and Mott insulator, it will dive down to 0. So that's why you say, okay, well, do I have cases when TC is significantly different from ideal gas? The answer is yes, especially if you have quantum critical point between, say, superfluid and Mott insulator for the integer occupation number for bosons. But you have to be very close to proximity of an insulating phase to suppress TC significantly. Generically, everywhere else, you don't have to bother. Now just 2D, because you can say, oh, in 2D, it's probably totally different. I have to admit to you that yes, in 2D, it is different in a sense that ideal gas has no transition temperature anymore. Everything says, okay, at finite temperature, ideal Bose gas will not produce a condensate. Then you say, okay, yeah, what happens? Interactions in this sense are the must. So I need repulsive interactions between bosons to have finite TC. And then you say, oh, but then necessarily TC strongly depends on interactions because without interactions, it's 0. Well, the answer is that the dependence on interactions, for example, on the scattering length between the bosons is double logarithm. Double logarithm is not a function, it's a constant. Because if I change something here by 10 orders of magnitude, the moment you take a logarithm, it's suddenly not that big, but then you take another logarithm and just good luck to change double logarithm by a factor of 2. If it was already 2, make it in 4 is almost impossible. You have to go, I don't know, from one number to another number, which is 20 orders of magnitude bigger. So double logarithm is a very, very big function. The rest, I would say, yes, okay, this is more or less universal. This one was, again, done numerically to characterize what number I have here. And in this sense, yeah, that's more or less accurate prediction. What you have to do if you have to do two-dimensional bosons, what will be your TC? This is more or less universal scale, density divided by mass, by dimensions. And this is just another number which I have to use to predict TC reliably. This is more or less, call it theory. And then people did numerical simulations. Those are the points. Again, density changes from 10 minus 4, 10 minus 3, 10 minus 2, 10 minus 1. This is hard spheres. So beyond 10 minus 1, hard spheres will try to create this, they will start overlapping. Again, you are close to the space when just bosons are left without the space left. So it's already very crowded space. And again, this formula is pretty okay to predict TC within 10% accuracy, you are doing fine. But again, because double log is not a function. So if I say, okay, well, this is my TC, call it, I know, 0.2. You will not be mistaken much, 10% only, if you go from density 10 minus 4 to almost crystallizing the liquid. Okay. So that's 2D, even though kind of the physics is totally different from 3D. More or less same conclusion. So if I assume that, well, okay, log is of 41, I can make, given the numerical data, I can get my, educated guess how to put something in the middle, and then plus minus, not a big deal. But same question. What happens if I add Coulomb interactions? Sometimes Coulomb interactions in 2D, people call it a log. It's not a log, it's 1 OR. So I'm trying kind of to be physical in the sense that, okay, well, it's not log, which is also sometimes called Coulomb interaction in 2D. So it's true Coulomb interaction, 1 OR. And we find pretty much similar picture. So if I take TC, this is my kind of dimensionless numerator, which you saw before. So it's like TC divided by rough estimate for degeneracy and divided by M. So in proper units, this is dimensionless number. Well, you see, if I introduce different values of RS, again, going from small RS, say 1, to RS equal 50, again, outrageously small density, a little bit further, and again, you face a Wigner crystal, because it's a very, very dilute system. TC will change, but okay, maybe on a scale of relative to this middle line, it will change by plus minus 15% or 20%, but that's it. I can predict TC reliably without paying any attention that the bosons are interacting. This is for the lattice when I can, again, have very strong Coulomb interactions. I have Hubbard U. Again, I'm here. Unfortunately, I cannot just be, any more inspiring for you in this kind of discussion, because the message is relatively simple. Once you form bipolarons, and if you can treat them as point particles, as bosons, TC is actually given to you for granted. Unlike everything in kind of conventional superconductors, when fighting for TC is an outrageously hard job. Unless you can, okay, have Migdal-Agterberg and interaction is there. But if you have a more fancy mechanism, it's very hard to predict TC reliably, and this is the most difficult job. In bipolarons, that's relatively easy. Once you form point particles, you don't have to worry about what is TC. But I'll say, okay, what you have to worry about, because what I write down here, M, assuming that the mass of the particle is known. I know the mass of the electron before interactions are switched on. I have no idea what is the mass of the boson. So this is written in terms of assuming that I know the mass of my bosonic particle. And that's where all the difficulty will go now. So that's more or less the picture. So if I want to go superfluid with boson, I don't need a mechanism, literally. Even though in 2D I need the repulsion, but you don't have to worry how this repulsion will modify TC. Just go with this estimate. Mass, which you have to compute, density, which is the density of your bosonic particles. Say it's electronic density divided by 2 if I form bipolarons, and some number. And you say, what do I put in 3D? Put 3.2, somewhere in the middle of all the changes I have. And in 3D, put 1.3, again, in the middle of all the changes I have. And you will not be mistaken by more than 20%. Okay, so which means the problem of TC is solved. Well, now just, it's time to pay attention. Okay, how far, where should I go with this mechanism? Well, I have 2 parameters left because I fixed the number for you. just from all the numerics, different models, lattice continuous, 2D, 3D, long range, short range. Okay, I know the number. Well, there are still two parameters left: effective mass and the density. Density is easy, okay, that's what's given to you. But I say, okay, well, still you have to pay attention. Well, because bosons are not point particles. Effective mass, I'll have to compute the effective mass of my boson, and this will be important. I'll just delay it a little bit. But what about the density? Well, I want to discuss the mechanism. At this point, probably let me say something. Hopefully, I never did this mistake before. There are no Cooper pairs in superconductors. The electrons can behave in a correlated way, but there are no pairs. Because in conventional superconductor, you say, okay, what is, naively you ask the question, what is the size of the pair? And you discover that you have maybe 1 billion, maybe 1 million, maybe 1,000 of other electrons in this volume. It's okay, what pair? Who of them is pairing with each other? Typical distance is 1 over Fermi. The sphere or the disk which you draw is much, much bigger than inverse Fermi. So there are tons of particles in the radius which you draw. With whom do you pair? You say, okay, there's nobody because they're all identical. So rather, in all conventional superconductors, you have to talk about pairing correlations. That is much better language and sometimes much less confusing and even more precise when you do numbers. That's why I say I refuse to call them pairs, call them pairing correlations. So we have pairing correlations, but now I want to discuss a mechanism when I really want to treat bipolarons as bosonic particles. Now I have to talk about them as pairs, but with some accuracy, my language becomes more accurate in terms of the calculations you do and everything. Still, they are not pairs in a straightforward sense of the word as you would have for bound state of two particles in vacuum. Again, everything is identical, and when two bosons collide, there is, of course, a process. They will exchange internal degrees of freedom between themselves. And that's why they suddenly change their internal structure. This will happen on a very short range, very fast. Looks like an effective interaction between bosonic degrees of freedom, but still they will know something about their internal structure. But imagine that when I form bound state between two electrons, it's a relatively shallow state. Suppose binding energy is small, so it's large radius. So I don't want to push any of the formulas which you have seen to the limit when density is such that my bound states start overlapping. Because the moment they start overlapping, I really have to switch my language from pairs to correlation. And that's when the job of computing TC becomes very hard. That's the opposite limit. That's BCS. That's the hard limit. If I want to discuss bipolaron mechanism with the numbers which I gave to you, I should say that yes, I should not go to densities high enough so the bound states will start overlapping. So that's one condition. I say, okay, if I want to discuss everything within the mechanism, when I can treat everything as point particles, my density is limited. So everything is fine as long as the size of the bound state, say, okay, R is the radius, the roughly one particle in the middle, the other one is wandering around. Well, if that's the picture, probably I am okay. If even they are further separated, this even better. Well, but the moment I just create something like this for almost all the disks, they all start overlapping with each other, I probably should stop because now I'm not responsible for the numbers which I was trying to give you. So that's why I'm saying, okay, well, estimation of TC, what is the best possible case I can do within the mechanism? You see that my TC is growing with density. It was density to power 2/3 or a linear function of density in 2 dimensions. You say, okay, to get higher TC, go to higher and higher density. Yes, you have your bipolarons, make more and more of them, and TC will go up. But at some point, you will have to stop. So I say, okay, I will stop when the volume per particle, the particle, I mean bosonic particle. So the volume for the bound pair times the density is 41. That's when I have to stop. Okay, that's why I have to care that this is a compact particle. So that's one ingredient which I have to put into my estimation of TC. If it's dilute gas, I'm done. I know the numbers, it's accurate prediction. But then I ramp up density to higher and higher value, but then I stop somewhere here. And this becomes not very precise because this is an estimate. It becomes an estimate that yes, if I go to higher density, I'm not responsible. At lower density I am, but this is roughly where I have to stop. Roughly means maybe TC is within a factor of 2 to this estimate. So that's what will happen next. I will push density to the maximum possible when the overlap just starts happening. The second ingredient in my TC is effective mass. You say, okay, yeah, but why not doing what we have in continuum? In continuum, you have a particle, but again, this particle is a polaron in general because it's already living in the material. Why not have a saying that, well, bipolaron has a mass of twice the mass of the particle? And the answer is, okay, well, you are living on the lattice and you have interaction effects. It's not because you have bound state and by Einstein relation, the mass of the bound state is different from the mass of ingredients. No, it's because you are living on the lattice and you have interactions. There is no Galilean invariance. Only if you have shallow bound state and each particle is more or less on a short distance, behave as a free and ultimately learns that there is another particle in the bound state, then probably your effective mass for the bipolaron will be roughly close to twice the mass of the ingredient. Otherwise, the mass of the pair is totally different from double M. And partially this is a problem. Just very short slide explaining how this has happened. Well, just imagine that I have tight binding Hamiltonian particles hop between the lattice. You expand it close to the bottom just to estimate what is the effective mass. So the effective mass is 1 divided by twice the hopping. Again, lattice constant is 1. And then you say, okay, imagine that I have strong attractive interaction, I form a pair. And this pair is well localized on one side. Now this pair wants to move. Well, the way how it has to move, I have a pair, empty side. First, one of the particles has to tunnel, according to my Hamiltonian. Well, I go to a virtual state when I lose energy U. Well, then I have to move the second particle to the same side and recompose the pair. Of course, which of the two particles can move, or if you want to take care of the bosonic occupation number factors, that's why you have here 2. That's the answer. It's second order perturbation theory process. The pair will move, but this is the effective hopping matrix element for moving the pair from one side to another side. Well, and you see, okay, well, this will be enhanced by the binding energy divided by hopping. So in principle, it can be much bigger than M1 if it's a well-defined tight bound state. The same will happen when we form bipolarons from electron-phonon coupling, but on a much more dramatic scale. But that's more or less the picture, for example, to keep in mind. And for bosons, for electron-phonon coupling, I'll just give you yet another picture how this is happening and why it can be, I know, well outside of binding energy divided by hopping, no, much worse. But this is kind of to have an idea that, yes, the effective mass of the bipolaron is totally different from double M. And you have to compute it. So those are the two ingredients which are, yeah.
The opposite limit when attraction is much smaller than T.
In this case, more or less, generically, the mass of the pair is twice M. Because you have approximate Galilean invariance at the bottom. And by Galilean invariance, yes, the mass of the bound state is double M. Now, just going back to my original description. So TC, no, don't worry, we know everything. I can go to density the highest possible because I want the highest possible TC. But for this, I have to stop when the density times pair volume, I'll make it 1 aggressively. Well, then that's what I have. Well, remember that the density times the pair volume, say it's in 2D. Density is linked to inverse radius, the typical radius squared of the bound state. So that's my estimate. Well, in 3D, I will write down something like this. That's the radius squared. I'll take it 3/2, so it's like volume times density equals 1. That's the density which I will plug into this expression. Well, and suddenly you see that well, the answer is pretty universal, just different numbers in 2D and 3D. Well, because in 2D, it was already density. Density is replaced by R squared, okay. It's 1 over R squared. In 3D, it was density to power 2/3, but density to power 3rd is also related to 1 over R squared. So we have this expression. So it's just different numbers. This number is 3 times bigger than this one, but otherwise, we are more or less done. What to expect for the largest possible TC within the bipolaron mechanism. As long as bipolarons form, go to the largest density allowed by the overlap, and this will be your estimate what are the best conditions to expect from this mechanism. Okay, but for this, you see that my many-body kind of calculation is reduced to properties of two particles, which are coupled to each other by some way. Can be direct coupling, can be coupling through phonons, which again requires a lot some work kind of to finish. But I have to compute properties of the pair, and this is it. And the two important properties of the pair are effective mass of the pair. Once you form bound state, it still has to propagate in a lattice, so I have to compute this effective mass. And I have to compute the typical radius squared for the pair. I have to know how big is the bound state. Once I have those two parameters, those I estimate for the largest possible TC. Okay. This is the framework. I would say just this is the framework to discuss. I didn't do any calculations, nothing was specific. I would say this is absolutely generic. If you want to discuss bipolaron mechanism, that's the picture. Calculation of TC is not even required. What's required is to know properties of bipolarons. What they do, what are their properties. So that's where the whole difficulty goes. And that's why all the discussion which we've had for many decades about the mechanism ultimately was linked to what are the numbers. You can suggest a model, you can suggest the mechanism. This was never finished, actually. So I would say this is what we did, but nobody was writing those formulas before. But without them, you don't know what is TC. And unless you compute those parameters for the model which you suggest, you have no idea how high you can go. And now just roughly before we just go to any specifics of the models, what to expect? Well, there are different things which you have to expect from this because I have in denominator, I have the product of two numbers. I was telling you that typically the mass of the pair will be much heavier than the mass of two particles unless it's a shallow bound state. So you say, oh, it's very good because the lighter the mass, the better. Just wait a second. I just told you that the mass is small when R square is huge. When it's a shallow bound state, your mass is small. Yes, you're happy. But then R square is large. And that's the typical picture of what you will observe if you increase, for example, some coupling, which leads to bipolarons. You can start somewhere here. For example, that's where the bound state forms. Effective mass is good, but R square is huge. TC is low. You keep increasing the effective coupling. And maybe the first thing, which will be the most important one, will be the mass will slightly go up, obviously, but the radius squared will shrink much more fast. And you will actually discover that maybe TC will go up because the bipolarons are getting more compact. So I can go to higher density easily without overlapping them. Well, but if I keep going with this, well, maybe my bipolaron will actually become, I know, compact on the size of one atomic distance. Well, but then the effective mass will keep climbing up with interactions. It will get, I know, you have created deeper and deeper bound state. It's more and more difficult to move it. And then large effective mass will start killing your TC again. So you can expect that probably the generic behavior of this formula, if I switch on the coupling, for example, to phonons, which will allow you to bind electrons, that will be the typical behavior of the curve as a function of the coupling number. Okay. I don't know whether I have slides the right way, but suppose I ask you, okay, what else can control and produce the same type of shape by simply changing whether the state is shallow or not shallow? Yes, I have coupling to the lattice, which leads to bipolarons, but what else? Not just imagine. Say Coulomb repulsion. Suppose I have a model which has Hubbard repulsion, not the long range, but suppose I have strong Hubbard repulsion. Because I am forming a compact state, first I worry about Hubbard repulsion. What Hubbard repulsion will tell you? Okay, well, suppose this is Hubbard U. When Hubbard U is small, at some Hubbard U, you will start forming a shallow bound state. But then I just started increasing, well, sorry. If you suppose I sit somewhere here. So I already have a good bound state. You started increasing the Hubbard U. What will happen first is that, well, the state will start losing binding energy. R squared will start slightly increasing, but it's a more shallow state. You will get huge boost in terms of the effective mass. You keep increasing U, and then you may find that, okay, well, we actually go to the maximum of the curve because you are increasing the Hubbard U. So read it as the following statement. Large Hubbard U can be very useful for S-wave superconductivity. Well, it's somewhat unrelated in terms of physics. It's totally different physics from what I was telling you lectures 1 and 2. Because I was saying, yes, strong interactions. If you take care of screening, ultimately, altogether, strong interactions with screening, it's potentially a superconducting group. This was one mechanism, and what I'm talking now is just totally different. There is no Fermi surface, no logs, none of the same physics. It's totally different setup. And still, it may happen that you introduce Hubbard U, it makes your state slightly bigger in size, and the gain in effective mass will overshadow the size of the bipolar is slightly bigger. So large Hubbard U can actually help you.
Can I think? But still, large Hubbard U is against forming bound state.
Yeah, and that's why it's helping TC.
Okay, but at some point you lose.
Of course, at some point, it will be the same dome shape. It will result in the same dome shape. Ultimately, I will lose the bound state, R squared will explode, and everything is over. Particles will kind of disappear according to this mechanism. I am simply just want to say, okay, well, when you discuss bipolar mechanism, you really kind of forget everything about previous discussions with Fermi surface. It's totally different. And that's why kind of the statement itself sounds counterintuitive, but the physics and circumstances are nothing like you have in the Fermi liquid.
Some estimation, what's the relationship between mass and R squared? I mean, if they were just inversely proportional.
Depends on the model. Only for the shallow state, you can argue, no. Only for the Galilean system and shallow bound state, you can say that the shallow binding energy equals 1 over mr squared. This relation is correct, but only for the shallow bound state. And it's coming from Galilean invariance of the system. So only somewhere here, probably you can relate the two. Once I go kind of to the peak of this, when the size of the bound state is comparable to the lattice distance, no, none of this will work. And again, depends on the mechanism, but in general, no. Probably something related to what you heard from cold atoms. You say, okay, I keep talking that, okay, well, bipolar mechanism requires that particles don't overlap, but you say, okay, yeah, what happens if they do? I cannot answer this question easily because the moment bipolar overlap, it's strongly interacting fermionic soup. What do we know about strongly interacting fermionic soups? Almost nothing except one system. There is one system which is called unitary Fermi gas. It's the system of fermions. Okay, spin up, green, spin down, blue. So I have a system of fermions, they interact with each other. But when up and down fermions approach each other, there is some, effectively, short range attractive potential with very small radius R0. Ultimately, you can take the radius of this potential going to 0, which means it's much smaller than the interparticle distance. And you make the potential well just deep enough to start forming a bound state. So the size of the bound state can be much smaller than the distance between the particles. The size of the bound state can be made bigger than the typical distance between the particles, or you just push the bound state out completely. But you keep the radius of the potential much smaller than interparticle distance, which means I can express everything in terms of the scattering length. That's probably what you learned from quantum mechanics for short-range potential. Okay, that's the system. What do you expect? Well, you expect the following. If the potential is very, very deep, fermions will pair, they will produce bosons, bosons will condense. If potential is relatively weak, this is standard BCS. There is some short range, literally read momentum independent attraction between the fermions, but it's weak. That's precisely what Andrey was saying was solved in 60s by Garkov, Melik, Barkhudarov. You have universal expression for TC in terms of the scattering length, and Andrey gave you the expression. So that's what you expect in the opposite limit when the bound state disappears. It's still superconducting, but by the BCS type mechanism. Okay. Now, this is the typical, say, wave function of the pair in relative coordinates. So just suppose I just take the origin of this particle. Okay, how far away this particle is around this one when I create a shallow bound state. It's very extended. It decays only as 1 over r. When I'm just right at the edge of forming a bound state, that's pretty shallow, pretty weak decay. So talk about pairing correlations, because if the wave function dies out as 1 over r, sooner or later you'll see other particles pairing correlations. So this is precisely what's known as BCS-BEC crossover. Looks like you have a very nice model. When you increase interactions, on one limit, I have I will not call them bipolars. I have molecules because fermions form a boson. That's one limit. And then you simply keep changing interactions. You go all the way when the bound state disappears, and you go to pairing correlations. And then you go to BCS type state. And you have tons of particles inside the correlation radius. Okay, so this is called BCS-BEC crossover. It was actually already discussed by Leggett in the early 80s using some mean field considerations, more or less trying to argue that you can go from one limit to the other limit, even though this was kind of not a complete theory, but kind of mean fieldish type expression. It was smoothly interpolating between the two without the phase transition, which means BCS physics can interpolate slowly to the BCS physics, BEC to BCS in a smooth fashion without phase transition. You break the same symmetry, so there is no good reason to have a phase transition. Okay, so those are the parameters of the model. That's what we know. We know this limit. I already told you. The moment you have very well-defined bound state, you have bosons, and bosons will simply saturate. Well, again, Fermi energy is it's the same. Fermi energy scales as n to power 2/3. So that's more or less making a slightly different dimensionless parameter. So the dashed line is precisely the BCS, ideal BCS formula. So that's what you have for very deep bound state. Once you form a bosonic pair, you say, okay, why don't you make them phase separate? Well, that's because of the Pauli principle. Yes, two fermions attract each other, they form a bound state. Then you say, okay, why not more fermions come closer because they also attract? Yeah, but that's where the Pauli principle becomes important. You don't want, because once you form a pair up and down, the other pair also has up and down. Now, if I want them to get closer, then two up fermions will get closer in real space. And this Pauli principle ultimately says those bosons will repel each other. So I have a repulsive boson gas here. Again, it's calculated through the effective exchange by fermions between the bosonic particles at short distance. So we have, this is ideal gas TC. And we just keep going, keep going, keep going, keep going. And more or less we arrive to this point. Yeah, this point was calculated numerically by diagrammatic Monte Carlo. We know what this answer is. But that's when the bound state disappears completely. So that's when two particles in vacuum will no longer create a bound state. So that's the infinite R squared. I'm trying to limit my discussion to here. I say I don't want overlaps. And that's what I'm going to use, ideal gas expression. You say, but once you start overlapping and even strongly how much TC will suffer in this particular system, which was solved by 30%, you will suffer, but not more. Of course, then it will just start dropping exponentially. So even if you overlap in this system, not a big deal. Probably the second issue would be, okay, should I worry that TC is much bigger than binding energy? We know that we should not worry about this as well, because binding state will disappear here. TC is still very large, so it's infinitely bigger than binding energy. Well, somewhere in this region, they are comparable. So I don't necessarily have to freak out if I predict TC, which is slightly bigger than binding energy. That's okay. But that's what we know from this system. So that's naively my estimate, and I will stop here. I will not go further. But maybe in some system going further, it's not at all that damaging. But this is continuum. If I go to a lattice, we know something else, because on a lattice, many other things may happen. Maybe something else will be the following. In continuum, the mass of the boson is twice the mass of the original particle, but not on a lattice. Maybe once we start overlapping, the effective mass of how easily I can move and kind of reconsider, reshuffle bosonic particles becomes much easier. Maybe TC will keep going up as a possibility. I don't know. That's what I'm saying. Scenario A is not excluded. Well, scenario B will be more or less the same as I had on the previous slide. It's simply expressed differently. This is density. That's why the whole curve is increasing instead of being flat. Because I plotted not in terms of potential, but this is density. Remember, as a function of density, I always increase as n to power 2/3. So that's where I make my estimate. Maybe it can go up because particles will get lighter. Maybe it will go down, as we had in the homogeneous and the unitary Fermi gas. Well, maybe close to half filling, you actually create an insulating state. That's why it's going down. And this was actually established numerically that close to half filling, those bipolarons, if they're heavy enough, they may range in a charge density wave. Because remember, if I have heavy particles and they interact and the space is crowded, why not forming a crystal or on a lattice a charge density? And actually people do see it happening. Okay, so I'm not pushing beyond the dashed line. So that's more or less the qualitative picture of what goes into the mechanism. I think beyond that point, I will be slightly more quantitative. So any questions at this point? Yeah.
Would you have a crystallization at a fractional commensurate filling? Why only half filling?
Or half filling is for very simple reason. It's a crowded space.
But it's a question of.
Well, because if I am in a dilute case, but not at the level of Wigner crystallization. So if I'm in a dilute case, why not moving around, enjoy kinetic energy? But once I'm crowded, kinetic energy is already more or less exhausted. So the question is, what about potential energy? And if my particles, especially if bipolarons are heavy, any residual interaction will say, oh, it's probably a good reason to start organizing them in a way which minimizes potential energy. When they were far away, potential energy was not that important, unless it's Coulomb, but Coulomb goes to extremely low densities to form a Wigner crystal. Of course, with heavy masses, the notion of RS is not density 10 minus a very small number, because Bohr radius is defined in terms of effective mass. So the Bohr radius in this case just gets much, much smaller. All of this is important. So I say, yes, probably Coulomb interactions will create a Wigner crystal. Game over. But for this, I need low density. But in the crowded space, there are many other lattice reasons why this may happen. Yeah, so essentially, if the mechanism works, so I don't have a crystal, I don't have phase separation, because this is another issue. When I say, okay, well, I solved the problem, but all I have to know is properties of bipolaron, mass and the size. You say, okay, well, but I didn't say anything that those bosons will repel each other. What if the repulsion between bosons is not strong enough and they try to phase separate? Good concern. I'm not going to answer it because it's a totally different calculation, but there are two considerations which partially kind of save me. In all calculations which I will present, you can easily add Hubbard U as a repulsion. Coulomb repulsion, no problem. I'll show you that, okay, it doesn't cost you anything to calculate properties of bipolarons in the presence of the Coulomb repulsion as well. Both will, and Pauli principle. So Hubbard U, Coulomb repulsion, and Pauli principle, they all three work against phase separation. Pauli principle says, well, even if I have two bipolarons close to each other, they probably will not like it because I have similar spins approaching each other. Coulomb interactions, of course, prevent phase separation, period. They can produce what's called droplets, but global phase separation is not allowed anymore. So that's the nature of the Coulomb forces, it's extensive energy. Hubbard U will also do the same. It's okay, if two particles approach each other, the space is limited for how they can fluctuate. Probably this will also produce effective repulsion between the bosons. Even though the pair can overcome Hubbard U, having more particles nearby probably will still be repulsive. So those are the reasons I'm not answering those questions. I'm assuming that bosons are repulsive. Now just more or less kind of the canonical picture. What do I mean, say, by, say, first, polarons? For polarons, I mean the following. You have a particle, but then you have an environment, for example, phonons, and then they couple to each other. What emerges from this setup is a new particle with new mass and new properties. So that's the typical discussion of polaron. The most canonical models will simply say, okay, you have an electron sitting on side I. If I displace an atom on some other side J, there is some coupling, your energy will change. So this is called density displacement coupling. That's how you write it down, more or less generically, density displacement coupling. Of course, you say, okay, yeah, to simplify the model, and that's what happens next. People just make it bare bone. They just say, okay, let's forget about everything. Let's have one coupling constant, because otherwise I have many of them. And this coupling constant simply says, your strongest coupling and the most relevant one is when the electron is coupled to the atomic displacement on the same side. For simplicity, people also consider dispersionless phonons. That's what I have here. And say one phonon branch just to understand the physics. Okay, so this is what's called Haldane model. On-site coupling between the electron density and the atomic displacement on the same side. The more general picture, which is here, I'll just try to illustrate it by the cartoon. So it's ideal lattice. You put in the electron and every atom in the vicinity, because the electron charge is pushing on the ions, probably they will just be displaced from their equilibrium position. If I don't move the electron, that's the optimal energy configuration. If I don't move the electron, then my Hamiltonian is literally displaced harmonic oscillators. So that's what's written here. Except for the picture is for everybody nearby. The Hamiltonian itself, it's displacement on the same side. But otherwise, kind of same picture. So the picture is more generic for something like this. Well, but now just, that's good. But remember that, well, okay, when atoms are sitting here, they're quantum mechanical particles which are vibrating around the equilibrium position, and their wave functions are Gaussians in the ground state. In the shifted harmonic oscillation, well, they're still Gaussians, but around a different point. So, but when you displace a Gaussian from one position to another position, outside of the typical Gaussian width, the overlap between this wave function and this wave function is exponential. It's exponentially small. So displacing an atom well outside of 0-point motion will result in the exponentially small overlap integral. You say, okay, why do I care? I gained energy by putting an electron here, I'm happy. Well, but it's not moving. But if I want to move this particle, you see that every single shifted harmonic oscillator has to shift to a different position. Which means I cannot move an electron without reconstructing the lattice if I want to stay at the same low energy. Because if I don't shift my atoms to the same shifted positions, optimized, I probably equivalently excite phonons, because this is now an excited state of the lattice. So, but if I want to move without exciting the lattice, I have to reconstruct every single wave function of atoms around the electron. But reconstruction requires that one Gaussian has to go to another Gaussian. But if it's shifted far away, it's exponentially small overlap. So expect that at strong coupling, this type of model will give you exponentially heavy mass, not for the reason of having large binding energy, but for the reason that moving at low energy and reconstructing the lattice with small, especially with small vibration frequencies, is outrageously difficult, exponentially difficult. That's what in this case will result in exponentially heavy masses. Hopefully I explained it well. Any question? Okay. So that's more or less an illustration of what I was trying to say. Suppose you take an electron, but you say, oh yeah, electron is very fast to begin with. You say, oh, suppose hopping of the electron is much, much bigger than the phonon frequency. You say, yeah, but if you inject an electron in a lattice, probably it will never deform the lattice strongly enough. Yeah, if I keep it on this side, atoms will go away, shift strongly, but the electron will escape before this can happen. So you inject an electron, electrons start running like crazy, and the lattice is never strongly disturbed. So you say, oh yeah, let's consider this. So I have an electron at the bottom of the conduction band, and then coupling to phonons will be done perturbatively using conventional second-order perturbation theory. You estimate the energy. So if I have one electron is sitting at the bottom of the band, if I have two electrons, okay, they're sitting at the bottom of the band, it's minus W. And then you can do second-order perturbation theory, okay, how the energy changes because they couple to the lattice. And that's more or less, oh, sorry. I don't know where it's go. Okay, I'm already here. Okay, probably I decided not to bother you with the expression, which is second-order perturbation theory. You have an electron at K, it can emit a phonon, go to momentum K prime with emitted phonon. You sum through all the Brillouin zone for K prime, it gives you denominator for the W. So which means the correction here is given by lambda in the kind of notation which we had before. It's dimensionless electron phonon coupling times the bosonic frequency. So the dominant contribution to energy is the bandwidth. This is just lambda W0. If you do second order perturbation theory. But then you say, okay, yeah, but let's do the opposite. Let's just stop an electron and do allow the entire lattice to relax. Well, it's exactly solvable, shifted harmonic oscillator. For the shifted harmonic oscillator, the energy will go as minus 2 g squared over omega 0 squared. And in terms of lambda, probably I didn't introduce the notion of a lambda. Okay. Well, to get the lambda, I have to divide by W, that's what is called lambda, and then multiply by bandwidth. So what the estimate here says it will be roughly minus lambda times the bandwidth. And that's the difference. Here I already have bandwidths for nothing, just because they're delocalized at the bottom. But I barely have any correction from interaction. Here, the gain from interactions is related to lambda W. But they're not moving. There is no gain in kinetic energy. But I immediately see, well, there is nothing I can do about this one. The bandwidth is fixed. But this one will simply get bigger, bigger, and bigger. And when lambda is a Fourier unity, I will get a state which is low in energy. That's when you start forming bipolar ions. The energy of the almost localized state is much bigger, much kind of better than the energy of two electrons in the band. Then you say, okay, what is effective mass? Well, the effective mass by this consideration says if you localize two electrons and they have better energy, if you want now to move them, you have to reconstruct the entire lattice if you want to stay at this energy. And that's precisely where this overlap kicks in. You can compute the effective mass in this case, but the effective mass will scale roughly, like lambda W divided by phonon frequency. And if it's a big parameter, right away you go to bipolarons, your effective mass is exponentially heavy. And that's the problem with the bipolaron mechanism if I use this type of model. Yeah, so this is just a comparison of two energies which I presented before. That's what you gain from interactions if you don't move. That's what you gain if you move. Well, and the balance will switch when this parameter is bigger than 1/2. It's different from Migdal-Ashberg kind of expression because it's not based on the density of states. It's based on the Hamiltonian parameters. Okay. And I already more or less answered the question. When you switch from band type behavior to bipolarons, when you actually form a bound state, you actually form a bound state which is exponentially heavy. In a very narrow region, when it's shallow, you can play the game, but then if it's very shallow, it's very large R squared, it's not a big deal. But if you go to relatively compact state, it's already exponentially heavy. So essentially, yes, the estimate would be that, well, okay, the maximum TC in this mechanism, which you can expect, will contain very large parameters. Once you form the bipolarons, they're already exponentially heavy. Looks like we're dead. And again, if you try to solve typical models, you compare Migdal-Ashberg theory, then you say, oh, Migdal-Ashberg theory collapses to bipolarons. Let's estimate TC for the bipolaron mechanism. Given the Hamiltonian, the answer is it's not going to help. Those electrons are those bipolarons are simply too heavy and the TC will simply go down. So that's why I'm saying, talking about the mechanism and the possibility of producing high TC using the bipolar mechanism ultimately boils down, okay, what is your Hamiltonian? Did you solve the problem? What is the effective mass? And once you kind of do this job and finish everything, probably you will end up that this is not helpful. Probably just very quickly, we have other models of electron phonon coupling. One model of electron phonon coupling, for example, can be the following one. Electron can hop from one side to the other side, but the electron hopping itself is different depending on how some of the atoms are displaced between the two sides. Well, just as a cartoon, and this cartoon was pretty popular in the literature. I'll tell you another kind of story from my childhood. So the electron wants to go from side I to side J. Somewhere in the middle, for example, you have a couple other atoms and they're vibrating. But the electron has to tunnel from I to J. If those two atoms move away, you are happy and you can tunnel. When they move closer, you are not that happy because you have to go through them and your hopping goes down. You say, okay, well, looks like a good model. It simply gives you an additional piece telling that your hopping is modulated depending on how something is vibrating in the middle. Literally, more or less, the argument will go as follows. You say, yeah, I have hopping matrix element, which depends on the displacement. You have to tunnel through some barrier. Well, okay, if you have a barrier and the particle has to tunnel, it's exponential and there is some action, how the particle penetrates some potential barrier. Well, and because I'm saying, okay, well, those two atoms interact with the electron, the potential depends on X, so your tunneling action depends on the X, and that's the model which you have to solve. And then you say, well, maybe it's too tough for me to solve this model. Instead, I will start solving this one. This was very popular in literature, again, with many papers written. What's wrong? Well, apart from you say, okay, probably you go slightly away from the Taylor series expansion, which is allowed for the exponents. Well, the problem is this will never change sign. This is still the same sign. This will change sign. If G is large and X is dimensionless, kind of in terms of 0-point motion, it's B dagger plus B. So if X is a 41 or the entire piece here is bigger than 1, plus or minus, because X can be positive, can be negative, you change sign of the hopping, which is not even present in the original model. And then the exciting physics happens. Yeah, I have a colleague, Boris Svistunov, he's saying there is physics which is correct and there is physics which is exciting. So this is exciting physics. You go to large G and this model has outrageously unusual properties. But if you say that this model is representative of this one at strong coupling, this model has nothing of this. Okay, I'll just not go further. But there is another chance of how you can generate a model similar to this one, and this requires Markov orbital. Maybe going slightly, I don't know, to Daniel, that yeah, one band is not always the answer. Electron can hop from one side to another side. There is something vibrating in the middle, fine. But imagine that the electron has two tunneling paths, which are actually destructively interfering with each other. Then the argument is different. This tunneling path will give you sign plus. This tunneling path gives you sign minus to the hoppings. And the balance between the two depends on what happens in the middle due to vibrations of the atom. So literally you are doing now like this. Now the sign of hopping is not even decided a priori. So if the two numbers, T1 and T2, almost compensate each other, then maybe X is flipping the balance in favor of positive or negative. So maybe this type of physics can motivate me to study this model with exciting properties. Okay. Probably given the time, I will do the following. Let me tell you that we have very good techniques to solve bipolarons. And I will mention not this one, but the next one. Any Hamiltonian of this type, when electrons can tunnel between, say, nearest neighbor sites on a lattice, they can couple to atomic displacements on side I, on side J through arbitrary function f in this exponent. You can write down here anything you like. Okay, this is not sign alternating. It simply says, okay, well, you can suppress the original hopping exponentially, factor of 10 if you like. So anything here. Well, then electron density can couple to phonons on side I and side J by any function you like. Okay. And for the phonon Hamiltonian, I allow you to write down again whatever you like. Electrons can interact with each other on site, Coulomb repulsions, whatever you like. This Hamiltonian is exactly solvable. And exactly, I mean numerically with any accuracy you like. For this type of Hamiltonian, if I have one fermion or I have two fermions, which form a bipolaron, I'll give you numerically, call it numerically exact solution for all bipolaron properties. So this is done by a diagrammatic technique using X representation. So you really write down what would happen if I use the basis of real displacement of atoms and the trajectory of electron in the lattice. If you have two electrons, draw two trajectories. Potential energies are done through the exponent, so the sign problem doesn't come from it. Everything else is done through exact solutions for bosonic propagators, and you just simulate this type of graphs. They're sign positive. You'll do the job. You'll get all the properties of polarons and bipolarons, and you will know the solution for this Hamiltonian. So we have a very good handle of how this is going. And this is just illustrating what I was saying before. You can fix some coupling constant. And if I change the Hubbard repulsion, I can actually make TC higher. But I already explained why this is happening. You simply gain more in effective mass than you lose in the size of the bipolaron. Which means sometimes it can happen in this type of physics that Hubbard U is helping you to get higher TC. Let me now just discuss in the last kind of 5 minutes two other statements which are probably getting me to the conclusion of everything I was trying to present. I know I have to stop, but I'll follow every other speaker. Sometimes we say, okay, yeah, it's good that we can pair. Okay, with Cooper pairing, we already had an argument. Even if you have repulsion, don't give up. Maybe repulsion is just the beginning of the story, and much more exciting than immediate attraction. If you have immediate attraction, okay, the story is boring. You go superconducting, done. But if the original Hamiltonian has repulsion only, it's just the beginning of something more exciting. Maybe you'll discover how actually electrons manage to create pairing correlations out of purely repulsive. And we had a lot of discussion how this may happen in different ways, from Kohn-Lattinger to dynamic screening to whatever else. Here is another example. Now I'm talking about true bound states. It's not kind of physics coming from the existence of the Fermi set, Tuka Fermi oscillations or Tolmachov logs. No, I'm talking real bound states in real space. What are the other reasons? First, imagine that the energy how you couple to the environment is sublinear in the electron density. I'll give you the model right next, but just right now, just try to digest the idea. So if I have electron density concentrated somewhere, the energy goes up. So which means I lose energy because I couple to the environment. But the way how I lose energy is sublinear. Then you say, okay, well, if I have two electrons, I double the density. Well, and because of this effect, you immediately discover the following. For two electrons, I have whatever was delta square root of 2. But if I have them separately, this will be whatever delta. So n is 1, 2, and you discover that 2 is bigger than square root of 2, literally. But this immediately tells you that maybe if in the model, the way how you lose energy because you couple to the environment, not necessarily gain, but lose, if you lose this energy in a sublinear fashion, at some point, maybe it will be the reason to concentrate density and create bipolarons. Because this will be low in energy, just separating two particles far away. You say, okay, sounds fishy. Example? Well, tight binding Hamiltonian, Einstein boson. But now the coupling to oscillators is not linear, it's quadratic. So it's x squared. I'm definitely losing energy by being coupled to the environment because this is positive term. G2 is positive. I repel. Well, but then you immediately say, okay, what this term is telling me. If I have an electron localized, This looks like just additional piece to the potential energy of harmonic oscillator. Well, the ground state of the harmonic oscillator is given by frequency. Well, but this frequency, if I just write down this term in this way, you see that if I have electron density, it changes frequency squared. So the way how the frequency is changing, it's changing as a square root of n. So if my coupling constant is big enough, forget about 1. The way how you change frequency is square root in n. And the gain in energy is given by the difference of the harmonic oscillator in the ground state, which is softer harmonic oscillator, sorry, tougher harmonic oscillator, tougher, minus the original one. But the gain, the lose, how you lose energy is square root in n. Yes, you go to higher frequency, but this higher frequency is square root in n. So that's precisely when you start expecting that maybe at strong coupling electrons will form pairs. Actually, this problem was solved not first for the pair, because it's pure quantum mechanics. It was solved at the classical psi4 type model, except it's not psi4 because psi squared is standing under the square root. Because that's kind of the energy, and you try to say, okay, well, whether I can have bound state within this functional kinetic energy and the potential energy for psi. It's an equivalent of Gross-Pitaevsky, if you like, but simply this term has the structure of psi squared under the square root. This one has solitons, which says, okay, well, according to this picture, it's sufficiently strong coupling, it's a soliton. Do we have Swedish people in the room? Yeah. You will not be offended because we were trying to call this state, for whatever reason, when we started doing this and found those solitons in a quantum sense as bipolons, we call them Kuklons. Why? Well, because they were discovered by Toly Kuklov. We wanted to give him the fame. It was immediately rejected by the person who knew Swedish. No, you can ask the student what does it mean. Okay, I will stop probably at this point with one last slide. The picture that you can generate attraction between the particles out of almost nothing or repulsive keeps going. For example, this is one of the very early stories when people were thinking, okay, how electrons potentially can pair in the Hubbard model. Take the Hubbard model almost in Nagaoka limit when U is very, very large. So now U almost goes to infinity in the Hubbard model. How I can pair electrons, slightly dope the system. Well, this goes through the statement that, well, okay, if I dope the system, otherwise this is Mott insulator, which is antiferromagnetic state. If I dope it, the best way for the hole to behave in the doped Mott insulator would be to create a ferromagnetic region, because it can optimize its kinetic energy. Kinetic energy drops by the full bandwidth if I have sufficiently large ferromagnetic domain, because I can move coherently without disturbing the spin environment. Of course, I lose the domain energy. And you just go through the exercise, what is the energy of this bubble. You gain the bandwidth. Of course, you have localization penalty because the size of the bubble is finite. It's typical localization kind of drop, 1/r squared. And I also lose the domain wall energy because I go from ferromagnet to antiferromagnet. Well, you just optimize all of this and you get, okay, well, the optimal radius squared, which can be very large if the spin coupling is much smaller than hopping, which is okay for very large U. That's precisely what happens. Then you just do the calculation and you have the answer. But then you say, oh yeah, but if I have now two holes together, I can take this answer multiplied by a factor of 2. I can take two particles together in the same bubble and repeat the calculation. Of course, they will gain now twice the bandwidth. The bubble will be slightly bigger because I have to have twice the localization energy. Well, they can even repel each other, but in 2D, there is a very nice statement that effective coupling at low density actually goes to 0 logarithmically. So sooner or later, this will be more or less, I know, exactly 2. And then I also lose potential energy because of the domain wall. You optimize it and you find that, okay, very easily, if the bubble is large enough, you immediately have E2 less than twice E1. Which means if I dope Mott insulator with very large U academically, I will find that, okay, well, this hole and this hole will definitely want to form a bound state and form a ferromagnetic, call it bipolar. If the density is low enough, probably they will stay away from each other now because of the Pauli principle. So more probably, and they asked more or less to summarize what our lectures were about. All topics looks completely difficult and different. So starting from what happens in the Fermi liquid to ultimately how the Fermi liquid collapses, in this sense they are connected. But maybe the take-home message is repulsive interactions are not necessarily your enemy. Always pay attention, and maybe it's the start of much more exciting physics. And many things can be done with very high accuracy. We have some good understanding, apart from what happens in real materials. We are good with models, but we are still pretty lousy how to handle Coulomb interactions in materials. So probably you will change it. Yeah, thanks.
So if there's a model where the most stable bipolar has some non-trivial internal structure, say angular momentum.
In my case, the internal structure is trivial. It's just a bound state without zeros.
The question again, just.
I think the question was the way how I heard it. Is there anything interesting about the internal structure of the bipolar? In conventional electron phonon case, nothing special. Apart from maybe additional pieces which you can discuss. For example, if you have Hubbard U and it's a large size, particles have to avoid each other, and there are internal correlations in the internal state, definitely. So when we create bound states with large U, that's what you see in the particle-particle correlation function. The bound state is there, but they try to avoid each other. They are not coming to a short distance. They just try to stay on nearest neighbor sites, correlate, just to minimize the Hubbard U. Because when I say bipolaron, I'm not saying it's single site. So if my bipolaron is 4 sites, yeah, the particles can run around, never trying to get to on the same site. Still gaining energy from the deformation of the lattice, but completely avoiding U. So when the size of the bipolaron is large, and you have very large Hubbard U, infinite U, we also consider it infinite U. No, you do not destroy the bound state completely, even by infinite U, if the original bound state was slightly extended. Particles will simply create correlations avoiding each other, but still gaining enough from the lattice. So infinite U will not kill you. The second piece probably I didn't mention, sorry, yeah, I'll go for that. Probably you also know it. If we have Coulomb interactions, there are no shallow state, long R² states. When you have Coulomb repulsion and then you have attraction on top of it, usually we go through the physics, you create a shallow bound state, the binding energy goes to 0 and the size of the bound state goes to infinity. The moment you add Coulomb interaction, none of this is right. With Coulomb repulsion, when the bound state appears, 0 energy, it's already finite state. Maybe the additional piece, which may be important, I don't know.
Maybe to follow up on the last question, what happens if we consider a Chern band and then we have some electron that has some chirality? Can it also couple in some non-trivial way to the phonons and form some chiral polaron?
I would say probably I'm ignorant about the case because I never considered solving it. So which means, yes, if you have strange behavior in the band, typically still my physics, which I was discussing, you probably kind of read it. I'm talking about bipolarons only in the dilute density limit. So which means I have to stay close to the bottom of the band. Maybe this is the touching point. And then the properties of the bipolarons will be totally different. I have no idea what they are, and they can be unusual. As I say, in some models, there is a lot of exciting physics, but some models were never even considered. So probably you're right that under those conditions, I have to be much more careful what will happen. Yeah, I just don't know. Nobody was solving it, but I was writing down some Hamiltonian which was not containing it. I'm just afraid that solving it exactly, maybe I'll face the same problem, but I don't know. So good question, I just don't know the answer.
Maybe variant, so in conceptual question. You discussed BCS-BEC crossover within the bipolar domain. There is also textbook stories about BCS-BEC crossover, like in BCS, you pair and condense and pair condense at the same point. When it's BEC, fermions pair, and then there are strong phase fluctuations and condensation happens when phase.
Yeah.
In your story, is it qualitatively the same story or there's some quantitative difference?
No, I had two stories on two different sides. One side is BCS. Everybody say, okay, Garikov, Melik, Barkhudarov, done. My story was BC side. You say, okay, more or less trivial. You say, okay, it's ideal TC through the physics which you described. From the bosons, all the rest phase fluctuations, but nothing special, just ideal Bose gas. And then bosons condense and TC is known. And then there is a crossover between the two when everything is an interacting soup. For the interacting soup, the only picture I have is we have to go to 8th order diagrammatic expansion with conformal Borel resummation, which is fine-tuned to the branch cut, which is coming to the origin, and doing it properly with OTC. But we had to go through this nightmarish kind of solution to put a dot at the unitarity.
Very good. I was asking something more simple. When you show this picture, just for everyone to understand, there was also a blue line.
Probably I have to show it just.
Yeah, it's really more simple thing.
Yeah, probably I didn't answer correctly.
Yeah, so there is a blue line.
This one is the binding energy for two particles in vacuum.
Sure. And basic question is this. Again, compared with the pictures that some may see in the textbooks about BCF-BC crossover, is this blue line the one when pairs are formed? Or something different? Or it's the same line?
No, that's precisely the line. It's binding energy divided by Fermi energy.
So pairs are formed.
So pairs are formed below the dashed line.
It probably will go.
Which means I'll go very quickly. So essentially the entire region here, that's when you have preformed Cooper pairs, not Cooper pairs, preformed real space pairs, which later condense. Once I approach here, and this here, this is all phase fluctuations, density fluctuations, soup. This is all soup. And now you emerge with BCS. But yes, below the dashed line, you have preformed local pairs, and then you can treat them as bosons. Yes.
I have a question about that. Did you have an example model with like not proportional to like omega and B and B dagger squared?
Yeah.
How do I understand the nature of this model? Is it like proportional?
Oh, okay. Yeah. Well, this was in the context of strontium titanite oxide by the following reason. There is a very soft mode, but it's a transverse phonon. Well, you may remember how you couple two phonons. You couple through the derivative of the interaction potential. Electron couples to the ion. There is some potential. You differentiate it and you couple to X. Once you differentiate it in Fourier space, it literally says you have coupling which is Q times the displacement vector. Transverse phonon immediately says I'm orthogonal to this one. So if you want to couple at low momenta, because everything happens at the bottom of the conduction band for the electron. So if at low momenta I want to couple to this soft transverse mode, I have to couple through the X square expansion because the linear one, simply the coupling constant vanishes for small q. So that's the only reason. So say, okay, well, that's why this one goes to 0 because you couple to the transverse phonon. Sometimes you have other reasons. I just did it from some paper. Suppose the good coupling is to this atom, but the electron goes to the S wave orbital on this atom. If an electron hops, in which direction the atom will shift? Well, no electron or electron, and the electron goes to a spherically symmetric orbital on this particular atom. In which direction the atom is supposed to shift? None, because they're all equivalent to each other. The atom doesn't want to shift. Probably this atom now will couple differently to neighbors, and this will be just a different U double prime X squared. It will change the local frequency of oscillations for this atom, because it now couples differently to all other. So maybe for reasons of symmetry, the moment electron goes to a particular site, the important mode to which you want to couple is not shifted. It's simply changing its properties, say frequency. That's the motivation for people considering this type of model. Transverse phonons is one. The other one is for symmetric reasons. Maybe the strongest coupling is coming from this mechanism, not from the displacement.
That's
Yeah, it's day 4. Yes. Yeah.
I guess I should pick like that, right? Like the one. I'm going. Pair correlated. Other takeaway is bipolar.
In some model, they simply just go to the same site together and they hit.
You can leave out whatever you want, something bipolar, there's not like a real fast.
No,
Let's say back to balance, you can take over. Why, talk about bipolar on. And this one is,
Most
I was trying to find my explanation, I had two explanations for it.
Yeah, that's.
Well, where- where did they- This is one electron. You can pop. But now electrons gain energy by pushing them around. If I put the other one here, it will be very happy.
Wait, but the blue ones are ion.
It's like one.
That's different from great points.
Yes, so they're pushing.
If I push them even further away, it's even better. Look, you have m omega squared divided by 2 plus whatever coupling you have. Complete the squares. And the moment you complete the squares, you will get the gain.
Yeah, but.
It doesn't matter what is the sign here, because what we will do next is plus minus. And this will be based on g squared, omega in denominator, blah, blah, blah. Whatever is plus, we'll go to completing the squares, but the minus universally you pull it out, it's just the end of the game. No, whenever you have a displaced harmonic oscillator, you're literally doing this. This is quadratic, this is linear. No matter what is the size.
Then you see.
This one. So that's the resulting potential. Either this one, let's say one type of G, if you go this way, you displace this way. Either way, you lower the energy.
Yeah, I also tried to like square you like.
If you have this type of Hamiltonian, moving atoms away will gain you energy.
Exactly, that's.
The way it is.
No, because you see, you don't, you say, okay, I have it, but X can be positive or negative. So when atoms vibrate, you say, I will pick up energy by simply pushing atoms to the negative X direction. Whatever is negative for a particular type of mass. If it's negative, I will push them in the positive direction. I will push everybody in the direction in such a way that I will gain from this. Yeah.
So.
Pushing or attracting doesn't matter. Either way, I will gain energy.
Something slightly different, so I have to think about that,
Yeah, because that was going to be my like.
So
if you
unitary
say that S and P have the same form.
Probably it was before.
Essentially, I have only two elements.
Yeah, so then it doesn't matter, yeah, that does, it should matter.
Therefore, I'm just writing a sentence in terms of.
Yeah, so yes, in performance of that, you should make sure you have consistent choices of all those operators. And I have given you ways to attach it and can.
Because there is no RGB in continuum.
But you're right, if you're.
This is continuous Fermi system. There is no RGB, only continuous. Second, those two electrons, it's not just forming a singlet on every single side. No, it's a continuum. I simply below the dash line, I form a molecule. Just molecule, just pure molecule, nothing special. You have single particles, but if they attract each other, they form a molecule. And the molecule is a bosonic particle, that's it. Nothing more fancy.
So the operator is
Andrey, let's say something. Below the dash line, somewhere here, you form molecule. And then people call phase fluctuation, but protons at high temperature, they don't condense, suppose ideal goes a gas, not a big deal, it's just molecule. When DC is comparable to the binding energy, now those are very strong pairing correlations. Because you cannot say I'm in bound state with this one because the other one comes and they overlap and all particles are identical. I pair with whom? I have no idea. They're all identical and just have pairing correlations. They don't have pairs. And it's even much worse if I go here. Because here the size of pairing correlations is doing thousands of particles. Definitely you don't have pairs. It's very wrong language. On that side, you can talk about pairing correlations. There are no pairs. You cannot identify a pair.
So it's actually, it says squares to one. It just means it's a unitary operator. So the problem with the unitary.
Those
operator
are pairing
is to
correlations P and
multiply
minus.
By any phase.
But you
Yes.
pairing correlation, but yes, we keep talking this, okay, this electron K couples to minus P and they propagate, but then they go to P and minus P and they do it again and again and again.
Okay.
What do you mean? But it's in momentum space, it's not in real space.
Just one.
And usually when people start talking pairs, they want them to be in real space, for example.
Always do.
There is no except one. Super was solving the problem when electrons were not identical to each other. Electrons below this hemisphere, they were kind of some electrons blocking, the other ones entering the momentum. Then he was finding the Cooper pair.
So
In the Cooper solution, this was a Cooper pair. But he completely violated everything about identity of particles. Because according to his interactions, only those two electrons are interacting. Every all other electrons, even though they are identical by Pauli principle, but they are not interacting with them.
Yeah.
So this is kind of bizarre Hamiltonian, which was saying, yeah, if special electrons which couple, everybody is identical, they don't couple. And then you solve it, but.
Sorry, I'm looking at you just for 1 second. Daniel, quick question.
Now it's expensive. Hi everyone. Back. Our lecture on right? Yep. Very good.
Okay, good. Okay, let's continue. So let me start by going, there were several questions after my previous lecture, so let me go back a little bit and then we move forward. So going back a little bit means this. Also, it will be good to repeat what was in the previous lecture. The question was, why is there a simple reasoning? Why essentially, if we consider isotropic situation and we do Kuhn-Lattinger understood as the second order perturbation theory, we start with the situation when interaction has only S-wave harmonic and nothing else. We renormalize this interaction, obtain what we discussed several times, irreducible interaction in the particle-particle channel, and it occurs attraction in number of channels of which P wave is the largest one. One answer, it happens, right? I put calculation in the computer tells me, or I do it by hand and it still comes out. But there is some reasoning why it happens. And the reasoning goes this way, that again, isotropic system it will be also good to say a few words about isotropic system because the rest of the lecture will be about lattice system. So isotropic system, something that we discussed last time. And what we want to do is to obtain what we call previously, it was, I guess, with red color, irreducible vortex P minus P, of course, anti-symmetrized as it should be with respect to spins. But we know that we start with Hubbard interaction, right? And then start renormalizing. And when we do it to second order, again, let's write down quickly these 4 diagrams plus twice diagram like this, plus exchange 1. That's what we get to second order. There's just no other diagrams. It's all what we can write. Very good. And again, this all external momenta are k minus kp minus p. So it's this kp minus k minus p. And I put minus sign, which means anti-symmetrize. That's what we need to do. Originally, it will give you only spin singlet S wave because this interaction and this interaction is U, which is constant. Okay, to make long story short, if you are dealing with constant U, there is substantial simplification, which happens in the case that I'm considering. It happens also in majority of lattice systems as well. So all these modern studies of Kohn-Latinger superconductivity in various systems, twisted or untwisted, they also use the same what I'm going to say in one phrase right now. There is a cancellation between these three graphs. The argument is that there are two vertex correction terms. I can renormal, I can write it like this, or I can invert it. And you saw these graphs before. And there is a Stempel rule of diagrammatic techniques that every time you have a bubble, you have a factor of -2. And let's not discuss where it comes from. It's just rule of technique. So every bubble give you -1. Summation over internal spins give you another factor of 2. And as a result, there is a -2 here, there is a +2 here. Internal parts are exactly the same if interaction is a constant. Just don't make a mistake. If interaction is not a constant, there is no cancellation. But if interaction is a constant, this cancel out. And then with this one, it's something that we already know. Kp minus k minus p. But this guy gives you particle hole polarization as a function of k plus p, right? It's exchange diagram. This is what we already did. So as a result, only this term remains, and I have to anti-symmetrize. What it means? It means that I think we used to call it U tilde. Let me put it like this, which means irreducible interaction, and it will, of course, anti-symmetrize with respect to spin. It will be equal to original term will be U, let's put spin indices, alpha, beta, gamma, delta. It will be U delta, alpha, beta, delta, gamma, delta. Next term will be, you have to believe me about the overall coefficient. Let's define P as with positive defined quantity. It will be plus U square polarization of K plus P delta alpha beta delta gamma delta. And I have to subtract anti-symmetrized part. What is this? When I subtract U square polarization, let's call it particle hole here. What should I write here?
K minus P.
K minus P, not K plus P, right? Because I interchange these two guys, right? So this will be K minus P. And of course, it will be delta alpha, delta, delta beta gamma. We know what to do here. Take symmetric and anti-symmetric combination of these two guys, right? And let's look, just to make long story short, because there is an infinite number of things I want to discuss with you today. Yeah, we'll stay here until 7 p.m. So let's look into triplet channel. By the end, we said that the largest pairing turns out to be in P-wave channel. So yeah, question? Yeah, go ahead.
Is this cancellation also happening if you have a multiband, a multi-orbital system, and you have, let's say, U, J, and so on?
You have to check. But normally what happens, I know about situations. If you have spin full fermions, yes, every time I have this, there is a cancellation. There are situations that you are also familiar with when excitations in the displacement field in the presence of spin orbit, excitations are spin non-degenerate, but there are two bands. And then again, cancellation happens. So you have to check every time, absolutely. But you see it here. Okay, let's look U tilde triplet. You will see the message I want to take. There is nothing to take here because, of course, I have to also write down minus U delta alpha delta delta beta gamma, not to forget to, let's put it in brackets. not to forget to also anti-symmetrize the leading term. Very good. But we need to anti-symmetrize this one. And my story will be very simple. Its triplet combination will be u square over 2, p of k plus p minus p of k minus p. Right? The rest will be symmetric combination of spin indices, which is what we have for triplet. Right? Agree? Very good. Now, the whole story, big story, superconductivity, blah, 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 come from the fact that we have plus here and minus here, not other way around. That we deal with exchange diagram, and exchange diagram interchanges momenta to minus momenta. So why is this relevant? Because quite generally, let's put subindex particle Hall everywhere here, not to forget. Quite generally, if I plot p particle Hall of Q as a function of Q for isotropic system, when everything is rotationally invariant, and this guy depends only on modulus. You don't expect, as Nikolay already said in his lecture, you don't expect that in isotropic system, there will be a peak at some finite momentum. It can happen, but it's a very special situation. So you normally expect that this function should go down as a function of Q. I mean, logic is very simple. You're in an isotropic system. Why there should be some finite momentum at which normally it requires non-analyticity. We know cases when the function goes up, but every time it's related to some non-analyticity in the problem, let's avoid it. If you have this, I will do one more trivial approximation. Any function that goes down, if you close your eyes a little bit, can be approximated by Arnstein-Zernike form. So I'll just do it as 1 over some mass square plus Q squared. It's not that I have to do it, but it will just be there, right? Function goes down. And then I put it here. And when I put it here, let me do it this way. I'll put it here. What I get? I get u tilde proportional to u square. Actually, even I can write down u square over 2, 1 over m square plus k plus p, of course, vector square, minus 1 over m square plus k minus p. Oh, sorry, minus right squared. Right? Very simple formula. We all know how to take a difference between these two terms, right? And it will be minus twice u squared kp divided by two denominators which are both positive. And you immediately see minus sign, right?
But k dot p doesn't have a definite sign.
Sorry?
K dot p doesn't have to be positive.
K dot p is p wave component. It's cosine theta. It's p wave component of the interaction. So if you look at p wave component of interaction, of course, this immediately tells you that this is what you need, right? It will be cosine theta of k minus p, which is cosine theta k cosine theta p, plus sine theta k sine theta p, and this is exactly what gives you p wave. Of course, there is also something here, there is also something here. So generally have all odd components, right? Not only p wave, and it will be your task, not for Friday, but just for yourself, to make sure that all these components are attractive. But for p wave, I hope it's completely clear, right? Forget about this, forget about this. Let's assume that the mass term is the largest one. Then in denominator, you get m squared plus something, m squared plus something. This is definitely, to first approximation, just 1 over m to fourth power. This gives you p wave component and minus sign. Where it all come from? From the fact that you start with k plus p. It's exchange diagram that gives you the leading role. Let's just take it because we will discuss this later on. At this stage, let's just take this as a fact. Okay, very good. Let's move on. I will make several parallels with previous talks today. And in particular, let me start by going back to examples. And what I want to do, I want to look now into lattice systems, because essentially, except for Coulomb gas, pretty much all other systems are lattice systems that we study. And so with lattice systems, we have different story. We can connect story in lattice systems with isotropic systems, but this requires some care. Namely, in lattice systems, we cannot expand in infinite number of orthogonal components with angular momentum. It doesn't exist, right? For example, if we take a square lattice, that is called D4H group, which is basically what are symmetry operation in a square lattice. Rotation x goes to y goes to minus x, rotation by pi over 2, pi, 3 pi over 2, and 2 pi. And of course, inversion, x goes to minus x, y goes to minus y. And if you look carefully, you find that there is only 4 one-dimensional representations, which read it spin singlet, and 1 2D representations. This will be spin singlet. This will be spin triplet. Yes, you still can rigorously separate between spin singlet and spin triplet. These two will never talk to each other. So you take interaction, you split it as we did before into singlet and triplet parts. The two don't talk to each other. It means that you solve pairing problem independent on each. And you may have attraction in this, fine, but the number, how many components are here? Infinite number. Because you have to replace infinite number of components with different angular momentum by wave functions of your lattice systems. And let me do it here because this was more studied, of course, with respect to cuprates and then iron-based, etc. If you do it here, you find out that out of spin singlet channels, meaning that for spin we know that it's antisymmetric combinations, there are 4 representations that is called A1G, B1G, A2G, B2G, and A2G. What I will do, first of all, let me write down the table very quickly to you. The table should be, yes, should be here. What are operations? Operations that we have, so I follow Denis. I'll write table of symmetry operations. Operations are rotation by pi over 2. And of course, there is also rotation by pi, etc., but it will follow. Operation x goes to minus x, y goes to minus y, and then x goes to minus x, and y goes to minus y. And basically, the question is what are number of pluses and what are number of minuses under each of these representations. So the one that is called A1G, symmetric, just like S-wave, symmetric with respect to everything. The one that is called B1G is minus plus, plus, plus. B2G is minus, 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 plus. And then A2G is plus, minus, minus, plus. Basically, it's just simple combination. You have 4 operations, and you just combine 4 operations into different. Plus means symmetric with respect to this operation. Minus means antisymmetric. And of course, you can introduce infinite number of wave functions or states. Sorry, let me say accurately. Different number of gap symmetries or gap forms, sorry, which belongs to each of these representations. Just to make connection between isotropic systems that we did before and lattice systems, I will first of all introduce these components as I would do for rotational invariant system in terms of the angle. So I have some Fermi surface in this zone. I have some, this direction, say kx, this is direction ky, and I have angle theta with respect to, say, kx. You may say, what's the difference between isotropic system as this one? Who can immediately tell me what's the difference? Well, I know the answer, so I'm in privileged position compared to you. I know what I'm asking, yes? I know it's always difficult to answer this kind of questions. Fermi surface is not isotropic. Fermi surface basically obey properties of a lattice. And what angular dependence we can have for the dispersion? Epsilon k is equal to k squared, this isotropic part, plus say alpha k squared times function of the angle. Which function of the angle I can write? The one that it should satisfy all four conditions, right? Like it should have this symmetry. It should be completely symmetric, right? We cannot break the symmetry with dispersion, right? In terms of the angle, what it should be symmetric with respect to x to minus x, y to minus y. It should be cosine function, not sine function, right? And then under rotation of pi over 2 is also should not change sign. So what should be the function? Cosine 4 theta, right? Cosine 4 theta. Next term will be, let's say, alpha 2. I also put k squared. I don't even have to put it. Cosine 8 theta, etc., right? 8 theta is equally good as 4 theta. And you immediately see there's infinite number of them, right? So in this respect, when I look at this part, then my gap structures that obey that symmetry in A1G, it's either 1, meaning constant. Next term will be cosine 4 theta. Next term will be cosine 8 theta. And you know what it means. 12 theta, 16, etc. Right? 4n theta. For B1G, we need to have minus here. And very simple experimentation shows that it should be cosine 2 theta, cosine 6 theta, cosine 10 theta, etc. Equally here, it will be sine 2 theta, sine 6 theta, sine 10 theta, etc. Right? And of course, you see immediately what is left. Sine 4 theta, sine 8 theta, etc. Right? In terms of the actual functions that you study on a lattice, A1G give you, say, constant or cosine kx plus cosine ky. B1G give you cosine kx minus cosine ky. And for example, cosine 2kx minus cosine 2ky, it will give you exactly the same symmetry. B2G is sine kx sine ky. And actually, A2G is a product of B1G and B2G, which means cosine minus cosine times sine sine. Yeah. Okay. What I'm telling you, that now you want to solve for the gap. You have some interaction. We actually calculate this interaction using Kohn-Latinger, calculate it to second order, obtain interactions that have all harmonics, and we try to solve. And here is the story. First of all, I said, spin triplet and spin singlet are separated. Great. Let's assume that nothing interesting happens in triplet for the cases that we'll consider it's true. And we focus on these ones. Then we have 1, 2, 3, 4 representations, and we know what the states are. They still are orthogonal. So there is no coupling between, say, cosine 2 theta and cosine 4 theta. This term is out. But which term are coupled? The ones that are coupled through dispersion. Because when you calculate polarization bubbles, of course, you use dispersion, right? So each wave function or each gap function that differs by a factor of 4 theta will be coupled, which means that all these ones will be coupled in the gap equation. They will be separate from this set, they will be separate from this set and from this set. But each set has infinite number of components. As a result, you may take a deep breath and say you will have to solve infinite set of coupled equations for the gap, right? So how people deal with this situation? People deal with this situation in two different ways. One way is to, I need space here, so let me erase it. One is to say, yeah, I know all this stuff, but I have to do something, I have to publish anyway. So let me just close my eyes a little bit. Closing my eyes means that I assume that only leading component here is relevant, everything else will be numerically small. I mean, yes, I know that there is an infinite set of equations. I just truncate the set on the first term, and there are people who said, well, let's do it a little bit better. They truncate it at the second set. So I mean that they truncate cosine 1 and cosine 4 theta, 2 theta, 6 theta. So then you solve 2 by 2, right? You can still solve 2 by 2. This you can do. And this is where the statement that incorporates the gap is likely cosine kx minus cosine ky come from. That if you saw weak coupling story for cuprate Fermi surface, the ones that you extract from experiments, then you find that yes, to a good accuracy, for example, in this channel B1G, you get this form of the gap. In B2G, you get this form of the gap. Again, there is no accuracy here. There's no smallness, but numerically it works pretty well. That's number one. This works normally at weak coupling far away from any interesting physics. There is another possibility, the ones I already started talking about last time, but I want to now do more rational reasoning. When you focus on particular patches, when you say, well, instead of playing these games with many harmonics, what I want to do is to focus and take the same square Fermi surface, only instead of putting Fermi surface as not circle, but some, it's not elliptical, right? It's still x to y isotropic, but not circular. The Fermi surface that has cosine 4 theta, cosine 8 theta, etc. terms. I will put as the ones that people study in cuprates, these ones. Believe me that this Fermi surface can still be expressed in terms of a plus b cosine 4 theta plus c cosine 8 theta, etc., etc. Right? Particularly if you take these 4 pieces and move them as one Fermi surface around the endpoint, the corner of the brilliant zone, rather than being in the center. The center is gamma. So these states are occupied. It's like, it's called open Fermi surface. Doesn't matter. It still obey all these principles. Again, I can say I take this one, this is my epsilon k, right? This is where epsilon k is equal to chemical potential. This is my Fermi surface. Very good. I still can do all calculations. I still will get all the stories that gap components will be coupled. I can still say that let's take the first one only. And at weak coupling, I do get first component as the largest. But I can, as I said last time, and this was at the very end of previous lecture, we can do different things. We can say that here in the corners, density of states is the largest. And focus on what is called patch model. Consider patches. When I say that my gap, whatever it is, same in all corners or changes sign between corners, modulus of the gap, which I want to get, modulus delta, as a function of theta along the Fermi surface. Again, I can still introduce theta as the angle with respect to, say, kx direction. This is still ky, right? This is still ky. So as a function of theta, if the gap, I say this is where I expect the gap to be largest, then I expect that modulus of delta will be like this. It will be something around theta equal to 0. There will be something around theta equal to pi over 2, something around theta equal to pi, and for accuracy, something around 3 pi over 2. I assume this because I know that the density of states is the largest here. And you see this completely different approach. Instead of taking this harmonics
I take patches. I localize my gap in momentum space. Again, with the risk of asking you something that I know, but you may need some time to think about. What if I take this gap, notice this modulus delta, I didn't tell you which gap symmetry is, right? It's just magnitude of the gap. Question is this: if I take the gap like this and expand it in harmonics, these are eigenfunctions, right? I can expand in any number, any function in eigenfunctions, right? So suppose I take a gap, say, in A1G channel, means the gap doesn't change sign. It's the same in all corners. And I expand in harmonics. What do you think will be coefficient for this term, this term, this term, etc.? And I can do it for any channel, right? Give me a suggestion, and then I'll give you the answer. So again, sorry?
If it is delta, it's everything the same.
Say it again.
If it is a delta, the parts are the same. Everything is the same.
Everything is the same. You're absolutely right. So what will happen, and you can check it, almost the same, right? There's still some, it's not exactly delta function, but almost the same. So it's the opposite situation. Patch model is opposite to taking only the linear harmonics. With patch model, you assume that all harmonics are irrelevant, all come out with almost equal coefficients, and then out of this equal coefficient, you create, out of infinite number of sine-like or cosine-like functions, you create solution which will be like soliton. There will be solutions that will be picked at near particular. Yes.
So in these regions, so for major part of the Fermi surface, we are still assuming the order parameter to be 0.
No, by no means. No. We are not assuming this by any means. What I'm saying is that we assume it's the largest here. It's something here. We just try to obtain the largest one. And then if you want, we will connect them. No, by no means we assume that it's 0. No. Yeah. Okay. Look. Let's keep moving. And yeah. And then we do what we do. If we take this, and yes.
So in what sense the other limit is a big coupling limit? Because here, if you go to a stronger coupling in the interaction, states away from the Van Hoffs start to matter more. So it's also a weak coupling approach.
No, it's weak coupling in the sense that I will tell you. If you take even this Fermi surface and do second order perturbation theory, assuming that Hubbard U is small, Kohn-Lettinger. This is what we are going to do, in fact, but with patch model. If you formally do Kohn-Lettinger for constant interaction, you will find that yes, and then expand. You will find that, yeah, and sorry, be careful. If you don't consider that the density of states here is really strong, and just take whatever Fermi surface is there, when density of states varies along Fermi surface, but variation is not crucial, then you find that strong at weak coupling, it's either this or this or this or this, and with small corrections coming from other harmonics. If you assume, as we will do, that density of states is strongly peaked here, then you will obtain that all harmonics becomes almost identical, even at weak coupling. You don't need strong coupling for this. Okay, very good. Is this clear? Good. So here's what we'll do. We'll assume the density of states is substantially increased at the corners and focus only on what happens near the corner. Since I'm talking now about one-dimensional representation in spin singlet channel, necessarily my gap will be spatially even, right? So which means that if I have gap delta here, I will also have a gap delta here. And but I don't know what will happen here at this point, right? So far, I only know that delta of minus k is equal to delta of k. This is the requirement that I am in spin singlet channel. So let me call this gap delta 1, and let me call this gap delta 2, and then obviously this is also delta 2. And then I will quickly repeat what I did at the very end of previous lecture. Now, situation is more simple that if I would crank out all these coefficients and solve this infinite set of coupled equations, I can just say that graphically I do this. I introduce my trial infinitesimally small trial gap function in corners and check the reaction. How system reacts to introduction of infinitesimally small order parameter. I want to calculate susceptibilities. This is what Nikolay did in his first lecture. So what I will do, it will be very simple calculation because, so let me call it delta 1 naught. Naught means something very small that I put in. And simultaneously, I want to do the same in another region. Let me take different color. And I go introduce this quantity. And I call it delta 2 naught. So I introduce two infinitesimally small gap function, not knowing what the ratio between the two. I can take arbitrary, right? And see what the reaction will be. For this, what I will need to do is we don't need this anymore. So why don't we use this space? I will need to write down, as we always do, at least in weak coupling stories about superconductivity, we do ladder summation because we know that there is a Cooper logarithm coming from ladder summation. So we want to write down expression for dressed delta 1. It's equal to, we start with the bare one, let's call dressed like this. We start with the bare one, delta 1 naught, plus start renormalizing it, start putting it ladder series. And I will write ladder series like this. Just one choice. Do you agree that this is a full ladder series? This is what Nikolay discussed with you in his lectures. This is just what it means. That I put here bare one, then 2 times bare one, then 3 times bare one, and this give me full, right? Very good. Is it the only choice? No, there is another one. And another one will be this. And this will be red ones. I can do this as well. Why? Because look at this. This will be L minus L. This will be K minus K. If I put external as K minus K and do the same here, K minus K here. And the errors are, of course, moving in. And here I do the same. L minus L goes into this K minus K. So both are allowed. What I need two different interactions. This one and this one are different interactions. So let me introduce them. I introduce interactions which are, one is this one, when all fermions are close to this part, right? One, of course, near K, one is near minus K, but I go from K to some P or L, or some from L to K, put it this way, such that both L and K are close to this spectrum, right? And it's, of course, the same as if I did it with blue lines, the same interaction. There's complete symmetry between what happens near Kx and what happens near Ky. Let me call this interaction U1. I'm supposed to have 3 colors, but okay, I'll try. Yeah, there is probably something better. Very good. And also, we see there is another possibility to go from blue to red, or equivalently from red to blue. And let's call this interaction U2. So let me use the same color. Yes.
So the patches that you have drawn is between the Fermi surface. There is no Fermi surface there actually, right?
In patches?
Yeah.
Well, there is.
Or is it between the Fermi surface or what?
These are pieces of the Fermi surface, right? So I just want to be close to these points. Nothing else.
But patch does not involve any Fermi surface?
No, patch has a width.
Wait, yeah.
But patch is not a point, right? There is patch. This is the meaning for patch. Patch is some area.
Yeah.
Right? Okay, guys, is it clear what we are doing? And I hope it will be clear for everyone that I can also write down equation for the blue one, right? Oh, sorry. I can write down equation for the blue one, which will be bare one, right? Delta 2 naught. This will be delta 2. By the way, let's write down. This was delta 1. And this was delta 2. Now, equivalently, I can also write down plus all blue or plus from red to blue. Just like this one. Even more symmetric like this. Right? So now this one will be delta 2 and this one will be delta 1. Right? So I have a set of two coupled equations, delta 2 in terms delta 2 and delta 1 in terms of delta 1 naught and delta 2 naught. These two equations can be trivially, you can just do it yourself, can be trivially re-expressed in terms of delta 1 plus delta 2. Now I'm solving these equations. I know that internal part of this equation is the standard particle-particle polarization and it's logarithmical, right? So what we have here is that delta 1 plus delta 2 is equal to delta 1 naught plus delta 2 naught divided by 1 plus u1 plus u2 times density of states in the patch, whatever it is, times Cooper logarithm. Omega naught upper limit divided, we decided to put it as, we need to cut it either by temperature or by frequency. Let's cut it by frequency. And delta 1 minus delta 2 will be equal to delta 1 naught minus delta 2 naught divided by 1 plus u1 minus u2 times density of states times Cooper logarithm. Omega naught divided by omega. So far, I just summed up ladder series, right? I'm explaining to you BCS-like solution, but for two gaps. And of course, I used symmetric and antisymmetric combination of these two equations just because I factorized the equation into symmetric and antisymmetric combination. And this pretty much what I said at the end of previous lectures. That, of course, the ratio of full divided by bare is nothing but susceptibility, right? So we have two susceptibilities. I will just rewrite them immediately like this. This susceptibility, let me call it chi plus, equal to this, and this I will call chi minus, and it will be also 1. We divide full by bare. Full by bare, by definition, is susceptibility. You put something in, you check reaction, you divide reaction by what you put in. Very good. And then you see what's going on. That when both interactions are positive, we are talking about repulsion. Remember the last phrases from Nikolay's presentation. We want to understand whether repulsion is our foe or eventually will be our friend. So both interactions are repulsive. This is positive. This is positive. I just took them as two short-range interactions. Both are screen Coulomb interactions, and whether it's gate screen or screen doesn't matter. There is no way I can get anything here, right? This is positive, so denominator definitely never changes sign. But here, it all depends who is larger, right? So I can have, in principle, instability here in this channel, And we even know what kind of instability we should get. That if, it's a big question, if U2 is larger than U1, then chi minus diverges. Chi minus diverges. It's a reaction to delta 1 naught minus delta 2 naught when delta 1 naught plus delta 2 naught is equal to 0. So obviously, just think about this for a second. And this is what gives you gap function. Let's put it here. That if this is our Fermi surface, these are our patches. Fermi surface was like this. And the gap that I'm searching for is the one that will be plus here, minus here, plus here, minus here, which simply means delta minus delta, delta minus delta. This is the solution that we're looking at, right? And obviously, really obvious thing. This is, yes, we deal with patches, but patches are connected by an arc of the Fermi surface. So if we go from minus to plus here, we ought to have 0 in the middle. And this means that your gap has 4 zeros, right? To simple approximations, this cosine to theta gap. Equally, you can write down cosine to theta plus alpha cosine 6 theta. Right? Symmetry of the gap is what is called B1G or dx squared minus y squared, because dx squared minus y squared simply because cosine to theta is kx squared minus ky squared. That's as simple as this. Or more accurately, it's cosine kx minus cosine ky. But as I said, cosine 3kx minus cosine 3ky give you the same. Very good. So this is D wave. This is what has been measured pretty well in photoemission experiments, right? What photoemission, we cannot measure the phase of the gap. We measure only magnitude of the gap. So what photoemission experiments really measured was the gap function, delta, mod delta, as a function of angle theta. This was angle pi over 4, this point, and the gap was going like this. And there were points measured everywhere here. There were two groups. One did measurement first, but they didn't reach really 0. And it was really unpleasantly, it's not sad story, it's reality. Just 1 second. They had a theorist who didn't believe in D wave, seriously didn't believe. So they plotted their results as like this. As if there are two nodes, but not exactly at 45 degrees. This different gap symmetry. And then another group came and said, no, guys. It actually goes like this. So there's 2 lines going to 1 point. Then the first group redid their measurements and said, yeah, we agree completely. Well, the good thing that both groups got the same price. So both were recognized nicely. There was a question, yeah.
So is it the choice? Is it the form of the Fermi surface which determines which symmetry is stable?
In some sense, yes. In some sense, yes. It's a position of the regions where density of states is the largest. If by any chance, for example, if by any chance the position of the density of states would be the largest in this point, then you will get zeros somewhere here. And this would be called dxy gap, not dx squared minus y squared. So yeah, in this. Okay, very good. So we need to move forward. We really need to move forward. And moving forward means this, that so far it's great. The question is how to get there. Well, we said today we're playing essentially with Hubbard model. Then these are 2 interactions. And if I have Hubbard interaction, which will abandon probably half an hour later, but let's do it first. So if we take Hubbard interaction, then U1 is equal to U2 equal to Hubbard U. Right? Agree? Very good. And then you can say, wow, there's nothing here. It's 0. There is, of course, repulsion here. Forget about this channel. By the way, what this channel would give if these two terms would be negative. It would give you gap. If they would negative, then we would get gap in which delta 1 minus delta 2 is 0 and delta 1 plus delta 2 is non-zero. This is conventional S wave, delta, 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 right? So this is S wave for A1G channel. This is D wave for B1G channel. This is what we have. Within patch model, we cannot get A2G and B2G. For this, you really need to go away from patch model. Very good. So we don't get anything, but we know what to do. Then let's now do latest version of Kohn-Latinger, right? And when we do latest version of Kohn-Latinger, here is what we have to do. We have to write down to go from interaction U1 and U2, we need to go to what is we call, remember, we call it like this, irreducible interaction, the one renormalized in particle Hall channel. And this will give us either U1 tilde or U2 tilde, and tilde means that these are irreducible interactions, right? We don't worry about spins, we know that we have to antisymmetrize, we know all of it, right? Very good. So let's write it down. The number of graphs is pretty large, so I'll try to minimize this story. For example, if I want to renormalize interaction like this, this means this is irreducible interaction in which all fermions are near a particular patch, right? I don't have to include particle-particle channel, only particle Hall. So again, I can write down, I start with the bare one, plus I write down this, plus I write down this, plus I write down. Sorry? Sure, go ahead.
You have Hubbard U or not?
I have Hubbard U, yeah.
So which means the second one doesn't exist because you have to couple same spins?
No, but I have to.
Okay, so in your language, you will simply cancel them exactly.
They will cancel, okay, yeah. Okay. It's just diagrammatics which deals with antisymmetrization produced Pauli principle. Yes, please.
What kind of principle give us different views? Does it mean that it has to be like some type of structural pneumatic?
No. It's I can give you in advance what we will be heading to in hopefully half an hour. Let's put it. What's U1? It's interaction at small momentum transfer, right? It's this one. So suppose you have screen Coulomb interaction. Then this is screen Coulomb interaction at small q between these two momenta. When I can write down this small q, when I write U2, remember what it was? Let's write as U2. It was half colors, right? Then we have this and this. And the first term will be, we know, this two. We go from one to the other. So this is momentum q, approximately the distance between this point and this point. And you immediately see that this is nothing but pi pi. So another interaction is with large momentum transfer, right? If I take a survey, screen Coulomb interaction, which one is larger? U1, of course, larger, right? So we're cheating, right? We're cheating, yes, we are. But let's cheat first and then go back and say, well, we know how not to cheat. Cheating means let's assume that their screening is so big, that so strong that they're essentially equal. Here's what I'm telling you. And this is where we start actually story with this lecture and the next. There is a possibility of this one. It's not the only option. I'll try to keep two different colors. You can also do this. This is allowed. You can write down other diagrams. You can write more than this. You can write all of these diagrams by yourself. Two colors so you can know how to combine them. But every time you do this, you still have the same story. There's a factor -2 here, so this graph cancel out. You get polarization bubble here. You get This will also cancel out at the end of the day. So what you will get also, there will be also diagram like this. This also allowed. It's just like this one. But you see, every time you do this, yes,
Did you put in that the gap change is signed by hand?
only just a little bit louder. There is a.
So did you put in the gap change is signed by hand, or did that come from this chi-minus diverging? Which you feel.
Did I put the sign? Which one? Which sign?
So for your D wave, you say that the gap change is signed, this delta 2 versus delta 1 goes from minus to positive.
Yes, no, what I put, no, I didn't put anything by hand. What I said is that this is the channel which produces U. Let's put it here. Delta 1 minus delta 2, not equal to 0, but delta 1, let's see, delta 1 plus delta 2 is equal to 0, right? Which means obviously delta 2 is equal to minus delta 1. And this is precisely what I said. Plus minus means delta minus delta. Right? And then you are forced to change sign, to go through zero answer, right? Okay, so here is the story. The story is you get correction to U1. This correction contains polarization, particle hole polarization at small momentum transfer. Because look at this. This is K and say L, both are near one pitch. So this is particle hole polarization at Q approximately 0. You will get the same here. You will get the same here. This all will be particle hole polarization and momentum Q approximately 0. You may say it's K plus P rather than K minus P. Who cares? It's still near the particular point, right? So this is all particle hole polarization at momentum approximately 0. Good. And now we do the same for another interaction. The risk, what we can erase? We can erase this, right? And then there will be one simple but obvious thing, that if we start, let me try to write it using different two colors again. If I want to write down now this term and do the same calculation, right? Then you will find out that, for example, there will be a number of diagrams. But for example, you can write down it like this. This one, and this one. And then it will be like, just I will write down quickly. Yes, this one, and then blue one. And then interaction like this. It's one of the examples. You need to start with red, end up with blue. And you can only use red and blue. Either near here, near this point, or near this point. Right? By the way, why K plus P is 0? K minus P is obviously 0. They're both near the particular page. Why K plus P is 0? But you almost said this, right? Where is the page? Close to the point 0 pi, right? Sum them up, 0 to pi. 0 to pi is 0, right? So it's not only that they're near the same page, it's also important where this page is. The page is at the corner, right? Very good. Okay, now what is this? And bunch of graphs, write it by yourself. Find out that half of them are canceling out, but important that those who don't cancel contain particle hole polarization at Q approximately pi, because particle hole made of blue and red is the one with large momentum transfer, right? And so then we have interesting story. And despite that this story is really simple, this is actually the story that gives so many different superconducting orders correctly. And the story is that if you renormalize U1, you will get U1 tilde is equal to U1 plus I will tell you u1 squared plus u2 squared, or say u, let's start with u, simply Hubbard model, sorry. U plus u squared times particle Hall polarization, let's put q equal to 0. 0 or approximately 0, it's the same quantity, it's not singular. While u2 tilde will be equal to u plus u squared particle Hall polarization at q equal to less than capital Q, and capital Q is pi pi. And you see they're different. And then the question is, we deal with the lattice system. Remember, for isotropic system, I told you that you expect that particle Hall polarization will go down as a function of Q. It's not the case for lattice systems. So for lattice system, we need to calculate particle Hall polarization as a function of Q. And it turns out, and you will tell me what it means physically, that particle Hall polarization at capital Q is larger than particle Hall polarization at 0. Maximum is actually never exactly at capital Q, because I don't have really patch has a finite width. But within the width of the patch, it goes like this. Interesting, right? And at this stage, we just say, okay, this is what we can get, right? You know how to calculate particle Hall bubble, just green function of k, green function of k plus pi pi, integrate over momentum, integrate over frequency, you get what you get. We get this. Let's look first at the consequence. Consequence of this wonderful result is that this guy becomes larger than this one. So u2 tilde becomes larger than u1 tilde. And this is what we have to put here, right? Remember this, why we did irreducible diagram, because we said that you have to replace bare by irreducible. So what I really have to do here is to write it like this. Because what I do, I'm calculating a reducible vertex and then put it in a particle-particle channel, right? So now you see what's going on. Yes, this becomes negative. The reason why this becomes negative is because polarization bubble is peaked at finite momentum. You tell me what it is. Half of you presented posters on this.
Nesting.
Say it again.
Nesting someone.
Nesting? No, it's not nesting. No. Half of you presented posters of this.
Finite.
It's magnetism at the end of the day. You will find out that this is nothing but the consequence that the system wants to develop something different. The system also wants to develop spin density wave. This is why polarization at momentum pi becomes larger than polarization at 0. So this is the first time when we encourage something like, there is something interesting. System wants to develop something else, and this helps superconductivity, right? This how should we read this formula. Very good. Is this clear? Yes.
Could you please just clarify the definition of U1 and U2? We had the Hubbard U, but
Yes.
then U1 and U2 are just interactions at different patches, or how are we?
In Hubbard model, their interactions are the same, but I define them as interaction either within one patch or between patches. Renormalizations are different. Is this clear? Very good. Very good. So this simple stuff, right? Very simple stuff.
Question.
Yes.
Why would it be spin density wave instead of some other density wave for this?
Sorry?
Why would it develop spin density wave instead of some other density wave?
Because I didn't tell you why. I will tell you why. I'm just saying that what's your idea about what happens when particle Hall susceptibility start increasing at momentum pi pi? What it resembles you. Yes, we will figure it out explicitly. Very good. So then what are we going to do? We are looking at what time we have. And let's do one more thing. And then go to what we call RG, and then I will explain why we need RG. So far, this looks like good but simple story, right? We get pretty much what we expected to get. And with the advent of, actually, right, the story that I will tell you now resulted in about 100 papers about twisted bilayer graphene at the beginning of twisted bilayer graphene era, in the first year alone. This scenario is still called Kohn-Lattinger. But again, when you read Kohn-Lattinger in the current literature, it means second order normalization of interaction in a particle Hall channel. This is what it means. I forgot your question, sorry.
It was the same, like, why is this spin, where's the spin channel?
Yeah, okay, we will come to this, absolutely. But again, don't take me wrong. The word Kohn-Lattinger that you see in the titles of the paper means second order, normally starting with the Hubbard U, and then see what you get, what you obtain when you get second order. Second order generates you harmonics that were not present in the system to begin with. And then you check whether the harmonics are attractive or repulsive. Like here, what I erased. Remember, originally U1 and U2 were the same Hubbard U. I renormalized, U2 gets larger. I did calculation with you. So you have to believe me that it becomes larger. But let's take it. Okay. Let me give you one more example, and then we move to the case which I want to use an example of RG. There is a story why I said twisted bilayer graphene, etc. Story that I will tell you it's not twisted, it's just graphene. You know, the standard graphene, if you are at a charge neutrality point, graphene has a Dirac spectrum, and Dirac points, there's hexagonal brilliant zone, and so Dirac points are at the corners of hexagonal brilliant zone. This point K, this point K prime, and of course 3 other points are, this is still equivalent to K. The distance between these 2 points is a reciprocal lattice vector, and there are 2 non-equivalent points K and K prime. So this is K prime, this is K prime, and this is K prime. Right. If we are at charge neutrality, you know what happens. This is why they call Dirac points, right? The spectrum is linear near each of this point. If we put chemical potential right here, then all the states are occupied, all the states are empty. We have linear spectrum. We have this wonderful Dirac physics, which was studied to death. But you can, and surprisingly, you can even experimentally dope the system and dope the system substantially by putting chemical potential up or down. And when you do this, your chemical potential started going up, for example, up, you open up Fermi surface, right? How it happens in terms of brilliant zone. What happens is, it's very good to have colors. Originally, you open up Fermi surfaces like this. Let me, doesn't, let's do this. Small pockets near K and near K prime. Let's dope more. You put potassium and calcium on top and below this graphene layer. And this is, of course, big question whether it introduces disorder. But apparently, ARPES experiments tell you, no, you can still measure dispersion even when you increase the amount of potassium that you put in, and you still see what's going on. And what's going on is that, of course, when you dope more, Fermi surfaces grow, and eventually, when they keep growing enough, they touch. Let's do it this way. And then you have interesting story that is very similar to what we did last time, only now it's more accurate. And now we have really points where 2 pieces of Fermi surface touch each other. This is what is called Van Hoff point. Because if I dope a little bit more, then what will happen is that, let's do different color. The Fermi surface, now this is the Fermi surface, right? These are pieces. So 6 disconnected pieces of the Fermi surface now merged. And after that, there will be one connected up. There will be one connected piece of the Fermi surface like this. And then it will evolve further, etc., and nothing interesting will happen. At the point when this happens, in all the 6 points, density of states become logarithmically singular. This is what was called Van Hoff singularity. Van Hoff is always there, and the dispersion is just chemical potential is right at Van Hoff level. Means that I literally have a situation with patches. Now density of states in the patch diverges. Great. Very good. So what shall we do? We need to solve the same problem. The question is, do we get superconductivity out of repulsive interaction? Great. Play the game. First of all, how many patches we have? 1, 2, 3, 4, 5, 6. 6 patches, right? Good. We still look for spin singlet superconductivity. So which means K and minus K's will be equivalent points from the point of view of superconductivity. So this leaves us what? 3, right? So we have 3 different possible gap functions. Let's label them. How we do it? We do it, for example, here we get delta 1. This also will be delta 1. Let's eliminate all these points. Case. So this will be delta 1. Then let's do it delta 2. Let's do it delta 3. This also will be delta 3, and this also will be delta 2. Right? So now, yes.
What about the C3 symmetry? Does the gap not preserve the C3 of graphene?
Yes, but these are not points that are the distance between this point and this point is reciprocal lattice vector. The distance between this point and this point is not reciprocal lattice vector. So there are different points, not equivalent points in the Brillouin zone. So as a result, the gaps are generally different. So you have 3 gaps: delta 1, delta 2, delta 3. We don't know what the relation between these. How many interactions we have? We have, let me use different color. We have this, obviously, right? This will be, let's call it region 1, okay? This is also region 1. This will be 1, 1, 1, 1. And the same, of course, will be 2, 2, 2, 2, and 3, 3, 3, 3. They're all completely equivalent regions, right? What else I can do? Remember, I still want to look at superconductivity. So it should be K minus K goes into P minus P. So what I can have is this. I go from 1 to say 2. So this region 2, this region 2. I go from 1 to 2, from 1 to 2. K minus K, P minus P. Right? Or I can go from 1 to 3, or I can go from 2 to 3. Right? They're all equivalent interactions because points 1 to 3 are completely equivalent exactly because of rotational symmetry, right? So how many interactions I have? 2. There is no third interaction. I cannot write third interaction. Momentum conservation will not allow me to write 1 goes into 3 and say 1 goes into 2. This I cannot do, right? So interactions are still U1 and U2. We still have the same story, but there is one difference. Now we have 3 gap functions. So we have to solve 3 by 3, not 2 by 2. And it's interesting story, 2 interactions, 3 gaps. So which means that when I start again doing the same symmetric, anti-symmetric combination out of 3, I have 3 decoupled channels. What are the interactions in the 3 decoupled channel? There is channel 1, which is obviously will be S-wave because it will be completely repulsive. It will be, I keep U1 and U2. U1 plus 2 U2. There will be channel 2, in which interaction will be U1 minus U2. And then there will be a channel 3, in which interaction will be U1 minus U2. And here you notice, there are 2 degenerate channels. And in fact, they are degenerate by symmetry. So this is a consequence of having 3 gaps and 2 interactions. There are 2 degenerate channels. Interesting, right? If by, yes.
Why is the degenerate channels that choice and not the other choice?
Say it again.
Why is the degenerate channels those 2 and not the other one?
Because the one has U1 plus U2. There is no other channel with the same interaction. There are 2 channels with the same interaction, right? Degenerate means that if one becomes unstable, the second one will also become unstable, right? What are what are solutions if this guy again will be larger than this one? What will happen? Well, let's see what are the solutions. This we can figure out, right? These are our gaps. So we'll see what the solutions will be. Very interesting as these two degenerate solutions. Where are they? They should be here. Just give me a second. I think I have it here. Yes. Here we are. So this is our brilliant zone boundary. These are the points that we are interested in, right? Which are, right. So one is here, and one is here, right? This is 1, 2, and 3. And of course, in the other 3 points, solution is the same because it's spin singlet, right? So one solution will be interestingly like this. It will be 0 here. It will be delta and minus delta here. Obviously, then it will be also minus delta here, and it will be delta here, and it will be 0 here, right? That's one solution. I'm just telling you what will be the combination of these 3 gaps that gives us instability, say, in channel 2. In channel 3, we will get this. Ooh, we are behind the schedule, but it's okay. We do again this, and then it will be minus delta over 2, minus delta over 2, plus delta. Again, delta, and this is minus delta over 2, and this is minus delta over 2. Request. You know, I wrote 2 by 2 equations. So write 3 by 3, solve them, find this. It's really some elementary algebra, right? All you need to do is, right, this channel never realizes, right? So this will be delta 1 plus twice delta 1 plus delta 2 plus delta 3. Total will be 0, right? And total gap will be 0, and you need to find out what are the possible solutions. It will be 0, 1 minus 1, or minus 1/2 minus 1/2 1. Okay, game. We're playing the game. Game is this. These are patches, right? But remember, there was a Fermi surface. And Fermi surface was what? It was one goes here, 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 right? Very good. How many zeros I'll get along the Fermi surface for this solution? 3? No, the number of zeros will also be even. 4, right? Why? Because it's 0 here, right? There's 0 here. From minus delta to delta, or from delta to minus delta. In between, there must be 0, right? And the others are just here, right? What about this solution? Again. How many? 4, right? Where are they? Here,
Plus
right?
minus here.
Here, this is fine. Here and here, right? In our classification, if there are 4 nodes, what we call this gap has what? D-wave symmetry, right? Remember we said that B1G, B2G, this was wrong lattice, right? That was for circle, for square Fermi surface. Here is hexagonal Fermi surface, so it's different group, but classification is pretty much the same. There are 2 different D-wave representations. And this is D-wave number 1, D-wave number 2. Okay, we are approaching the final point. So we need to do 2 things. I will just finish rather quick. First, we start with Hubbard. In the Hubbard model, U1 equal to U2, this equal to U. This we start with this. So again, wonderful story. You can say nothing. This is 0. The solution doesn't develop, right? But what we need to do, we need to write down irreducible interaction, right? And then you get exactly the same result as the one we discussed before. Namely, you have U1, which will be U1 tilde, which will be U1 plus U1 square particle hole polarization at Q equal to 0. We need to regularize particle hole at Q equal to 0. Let's regularize it by finite frequency, finite temperature, whatever, because then still stays divergent. Or let's move a little bit from this line. While U2 tilde will be U1, U will be U, I'm sorry, U plus U square particle hole at momentum Q between patches. It's not pi, right? It's between patches. Between this point and this point, or between this point and this point.
Why one Q but two different ones?
Sorry?
Why not the sum of two different ones?
Because they are exactly the same.
They happen to be the same.
Yeah, they're exactly the same. Yeah. Right. Okay. Same story. I said same story as before. You calculate this polarization, and you get this. This is your capital Q. So again, polarization, particle hole polarization seems to, well, not seems to, is peaked at momenta between patches here, like it peaked at momenta between patches in the Fermi surface for cuprates. Anticipating what everyone has in mind, yes, it will correspond as the system tries to develop spin density wave with this momenta. Right? Okay, this was number one. But we're not done. We want to end lecture with something funny, right? Okay, you have, now we won. These guys become negative when I put tilde everywhere here. These guys become negative, these guys become negative. I developed superconductivity, right? The question, which one? This one or this one? Which one I developed? What do you think?
Chiral combination. In chiral combination.
Chiral means?
So it's a D plus ID.
Yes, you are absolutely right. So the systems then, what you need to do? You need to do either what Daniel said about fitness. I think it will work. But I did it in a very old-fashioned way. You introduce delta, you calculate condensation energy to leading order in delta, which is already in the order state. You check when condensation energy is the largest. And it's the largest when both solutions develop simultaneously. And the solution, remember, superconducting order parameter, generally delta, is defined with the F phase factor. Delta generally is mod delta e to I psi. We break U1 symmetry. So this order parameter has a phase, and spontaneous symmetry breaking is selection of the same phase for all pairs, right? So it turns out that for this order parameter, we can choose arbitrary phase A, psi 1. But for this one, then, we'll need to choose a phase which will know about psi 1. Because in condensation energy, this will be a term that depends on the difference between phases. And we need to maximize this term to get the largest condensation energy. And it turns out that psi 2 will be equal to psi 1, and then either plus or minus pi over 2. The two choices are completely equivalent. Condensation energy will be the same. Which means that in one case, if we call this delta A, and we call this delta B, the total delta will be e to I psi, which don't care, it's overall factor, delta A plus I delta B, and then there will be delta, let's say, I don't know how to call it, delta, one was already there, yeah, so delta C. Delta G will be e to I psi, delta A minus I delta B. So this is what comes out immediately from simple calculation. We don't need to judge anything. We don't need to assume anything. It all comes in. what we get, you already gave the answer. We get chiral superconductivity, which breaks time reversal symmetry. Why it breaks time reversal symmetry? Because the system chooses, now the system has to choose either this state or that state. By doing this, it spontaneously selects either I or minus I. If I apply time reversal procedure, this state goes into this state. By choosing one of these two states, and not a sum. Sum will be just either delta 1 or delta 2, or delta A or delta B. The system chooses such that both states develop, but the relative phase is either plus pi over 2 or minus pi over 2. So time reversal symmetry is broken, and it's also chiral state. Why chiral? Because you can see that one of the states is odd with respect to change momentum to minus momentum. So one is just like dx squared minus y squared, another one like just dxy. So you change x to minus x, one component changes, and then therefore it's the same change of like I changes to minus I. This is chiral state. So this is the state that people were thinking about for a while. It was obtained first for p wave, px plus ipy, or px minus ipy. This is a state that has Majorana states in the vortex course, and generally for each of the state, either delta A or delta B. Either delta, the end of the lecture, I'm rushing. Either the state delta C or delta D. If you plot any of the states, just combine this two, right? Take this one with factor of I, right? And then rewrite everything as modulus of the gap as the phase. It turns out that here phase winds by plus 4 pi. In this state, phase winds by minus 4 pi. Meaning that just write the state, and then if I'm not wrong, it will be delta E to 2 pi over 3 delta. This will be E to 4 pi over 3 delta. Oh, sorry, this will be, I need only 3 points. This one and this one, right? Sorry. Let's start with this one. This one will be some delta because I combine the two states. Then this one will be delta E to 2 pi I over 3, and this one E to 4 pi I over 3. So you make a circle, it changes by 4 pi. For the other state, it will be other way around, minus 2 pi I minus 4 pi I. So what you will get a state in which phase winds. They have all properties of chiral superconductor, and you get it for free. You get it immediately from Kohn-Latinger type description simply because you have 3 patches and 2 interactions. Very good. We're a little bit behind the schedule, so in lecture 4, I will start with normal RG study, but basically this is what we will do in next lecture. Everything is great, wonderful. If we say this, we start with the interaction, which is the same U1 and U2, so it's a bare level, not tilde, but on a bare level. There was 0 here. In reality, you start with positive value. So interaction at small momentum transfer is larger. So technically speaking, if you want to do it now, as Nikolay said many times in his talk, there is one thing the theorist wants, another thing is that nature wants. And nature wants interaction to be a screen Coulomb interaction. So generally we start with repulsion. The question is, can we go using what we did from repulsion to attraction without saying, yeah, we cannot go to strong coupling, but we want that much to go to strong coupling, so we close our eyes and go to strong coupling. We will not do this. We'll find that there are situations when already at the weak coupling, the system starts with repulsive interaction and then becomes attractive. It's called self-generated attraction, and this is where renormalization group study is must go. So this is what we'll do tomorrow morning, right? Okay.
We can take the questions. Andrey, for this last part that you presented, we started with the physics of 1/4 to introduce the dispatch model, but yet the Van Hoff part of it was kind of behind the scene, which is probably not important for this symmetry thing that you presented, but important for the problem on DC algorithm, right?
Yes.
So in this decoupling, let's say we have log, and then the top state, what comes out for DC and how it's different.
It
from-
basically goes like this. This guy goes as a simple log of something, let's call it omega naught divided by a still regularized log by something, by frequency, by temperature. And this one goes as log square. This is what it comes.
So second log is just a Van Hoff log.
One log is Van Hoff log, the second one is enhancement because the system is about to develop magnetic order. So this one.
I mean, if you solve it for TC, it is ECS like, but with the different dependence on the coupling.
Yeah.
Root of it or something like
Yes,
this.
it will be 1 over square root of coupling instead of e to 1 minus 1 over square root of coupling instead of e to minus 1 over coupling. Yeah.
Back to your Cooper story. Like you said, okay, if I get U1 and U2 attracted for free, let's close our eyes and assume that. Okay, and then you say, A1G channel is going to develop, right?
Yeah.
And so, okay, plus delta everywhere on the 4 patches.
Uh-huh.
I say, okay, this is this way. But is it possible that you can get like a combination of the, I don't know, 1 plus cosine 4 theta and it's still.
Yes, you can. You can.
I don't know
It will be exotic physics. The question was this. If it's A1G channel, can we get exotic thing? This is what Daniel called accidental nodes. Yes, suppose that you have interaction which has larger cosine for theta harmonic than constant. Then you get gap in the form delta is equal to some delta naught, 1 plus alpha cosine for theta plus higher order terms. Let's forget about them. When alpha is larger than 1, yes, you get accidental nodes. And that problem was discussed with respect to iron base as a possible source of accidental nodes in iron-based material. In cuprates, nobody discusses. Yes. There's
Model at small u, there is a piece where p wave has 6 nodes.
Yeah, same story. Yeah.
So is there some generic
Yes.
ingredient?
Only louder, please.
Is there some generic ingredient to get the nematic case and say as a function of temperature go from nematic to chiral? Is there some generic?
This is what you are asking. For in principle, yes. In principle, yes. You can, but for this you will have to go into. I think you will have to go into different pairing state. Not play the game with this particular Van Hoff points. I think with Van Hoff you can do it, but in general you can. You can go from chiral to nematic state. Yes. Essentially, nematic state is when you have these two states, but with not I, but real number. So either complex or real number. Yes, in principle you can, but I never believe that this is realistic. I mean that you do calculations, you always get I. Then you say, well, yeah, I have a parameter factor 2. Let me strike out factor of 2 and write minus 2. Then this is how it was obtained, essentially. So in calculations, you always get chiral state. If you look at the formulas and just replace something with minus signs, then you will get different. So I'm not saying that it's impossible. No, I'm just saying that simple calculation doesn't seem to give it.
What's the most interesting you can do, let's say, if you have electrically polarized light or playing with light by tuning between the two gaps in the state?
Well, in principle, you can excite either one state or the other. And this is what I think was done in some sense with a magnetic field. When you switch a magnetic field and you go from one state to the other. So I think this you do the same. You try to switch between different states.
But we want or the other.
It has to be one or the other, yes. I mean that if it's 2, then you go back to original state. Some of the difference of these 2 states are nothing but delta A and delta B, because conventional superconductivity. It's just the same as to say one of the original state develops, another does not. So the beauty is exactly to create both of them together. And again, with a particular model with particular interaction, it's entirely possible that you do something more sophisticated and you do get a state which is only one of the two develops and the second does not develop. Which one? Again, spontaneous symmetry breaking.
For example, it went from square lattice to hexagonal lattice. So if you go above, like nothing new will happen, right?
How to go from square lattice to hexagonal lattice?
The way how we took here, we did it, no?
Right. But well, we did not go from, when you say go from one to the other, you don't mean continuously go. Yeah, sorry. Yeah, then let's say it again.
So if we went to the lattices with C8 symmetry, let's say, this is the best what we can achieve, chiral.
Yes. Because of these two channels are degenerate by symmetry. If you probably can have a situation when two channels are not degenerate by symmetry by breaking C3. Yes, if you somehow break C3, that's what you mentioned, then probably you will have two different, I just don't know about.
Yeah, I'm curious about, do you have any 1D analogy of these like two interactions and I mean the
And three gaps?
not three gaps, but maybe 1 and 2. I mean we have delta 1 and delta 2, and also we have like in 1D we know in the Latinger liquid if you want to form if you want to form superconductivity, you also need the large momentum. For example, interaction should be bigger than the small momentum interaction. In that sense, you will form superconductivity. Otherwise, we form like it will form charge density wave.
It's similar. I'm just trying to remember how to say properly. What you are saying is absolutely right. We will have the same story here. Only instead of charge density wave, we'll have spin density wave. There will be competition between the two, and then you see that competitors help each other when one order sets in, and try to kick out another order. Yeah, but in terms of connect, I need to think a little bit to answer about one dimension. I just cannot immediately wind up in my head. Yeah, maybe Daniel can answer immediately. Yeah.
I think the statement was that Latinger parameter, which direction it goes, to k smaller than 1 or larger than 1, depends on how
Okay.
depends on the number.
Yeah, but this is not exactly like two different interactions, right? It's just Latinger parameter.
That's how you classify in which phase you are, superfluid or not.
Yeah, but the Latinger
is a combination of two interactions.
Yes.
Okay, any more questions?
I think it was two interactions, different channels, but it's not all particle-particle interaction. I think the story was with interaction and particle-particle and particle-hole channel. The one that we do. Okay, let's do it this way. I will do RG next time, and you will see whether it's the same what you're asking or not. If not, then we'll come back to your question.
Okay. Thank you.
Okay, let's look at the magnitude of these chiral gaps. Do they not?
It's louder.
If I look at the magnitude of these two gaps that you give, does it ever develop a node? Doesn't seem like
No, absolutely not. Absolutely not.
Is that
Delta A plus delta B means that the gap that you put in the equation is delta A squared, square root of delta A squared plus delta B squared. They never go through zero together. So yes, they never do it. If it's only one, then of course there are 4 nodes. Yeah, and this is a chiral state. That's what you pay the price for eliminating nodes. It's what Daniel was also talking about.
Okay, any more questions?
Okay.
Okay, if not, then let's hang out for a minute.
Well, you can spontaneously break the symmetry. So it's the same, so you can choose basically either state that spontaneously breaks. So one anti-universal. No, see, Title does not break C3. This if it is thematic, then you break Q1 and C3. Yes, one is generally the case. Also, the only one that doesn't break is the it's this one, like the break.
So you tell me.
This one,
We don't know. What's the method you want to put X, Y, five? Oh, under five?
I was wondering, why can have chiral superconductivity?
Yeah, but it's
Because then, yeah, I mean, I
Yes, 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 according to my calculations.
Point with the gap.
watch it.
Really, yeah, not lying. Make this up.
Really?
Yeah, really. You look at it, you one right? One more. I myself also want
Yeah, so, but this fixes.
Yeah, I know, but we.
Yeah, definitely I've tried it.
It's basically, you have to put dimensionality. Then. Yeah, put dimensionality four.
That's how I went.
For A or for B? For A. Yeah.
It is called.
Then it's Yeah, but the gap vanishes and it's not superconducting. You need to put dimensionality four. So we were right in terms of the commuting. If it's commuting, we take the original energy. Yeah.
You.
And then write down like our argument, and then that way, then you can put it down. For example, 4 weeks is it's
It's open and you solve for you one so that.
Dimensionality 4 right, 3 is point, 2 is
and you substitute one is like instead I have 3 patches, right?
but yeah, if you're higher than 3, then it's like an average.
You want in terms of you want me to say delta 1 is just delta 1. No, it's not like it's open everywhere. Never running 0. You diagonalize it and you get the idea better. And it's manifest. You have unless they're overlapping, you have a
No, yeah, I understand, like, I mean, I followed that, like, you get the face, you get them as the, your maximum safe connotation there, you get the.
If every time you both one relative face, I think it's the relative face, I started.
Like, just like.
Yeah, so like if you have co-dimensionality of 2, right, so 2, 4, and 3D.
Yeah.
You make a line,
Correct.
right, but you add another one, right, to the, so the line from the,
Yeah, correct, and you got another one, but you can't
So
have
you don't
anything.
need a co-dimensionality for you only.
No, we make the point.
Yeah, maybe.
Section 4 is the one that.
Probably just guys to define.
You'd have to ask Luck knows the answer. I don't know the math part.
But how to put the hand in it?
Like we was working out yesterday and
I think it is co-dimensional.
Okay.
I think, and then if you use it, because they also recheck it through like the 10 representations or whatever.
Okay.
And then that's it, that same argument applies, right? You're supposed to end up with co-dimensionality.
Please.
I'm not.
I was confused now.
I'm not the correct person.
Well, but you should always.
There
should be a- Yeah, there should be a point right now.
Yeah, but can where we.
By not defining, so the only way that the gap is like depth side, the baseline side is not defined, it's only like without going zero. Okay, I see.
I'm not sure. That's part, I was initially asking, is it just zeros, but then I realized that there are no zeros. And I was like, what's giving me this space? Is there a singular point?
Factors, it would start from 0 at the level, but one to the factor.
Yes,
Will be like easier than we start from the constant.
of course.
So this is exactly.
This is the easiest case.
Oh,
Yes, this is the easiest case. And tomorrow we'll consider not the.
meaning the previous case, it's.
We also started with 0. In the previous case, we also started with 0. We started with exactly the same. U1 was equal to U2.
完全一样。
So we had exactly the same. The only difference is double the genetics.
不会让它真的变得很simple，就是有什么时候
王姐，你
Then we need to do some.
我的 paper 吗？
对啊，
怎样？
这个
Because
结
normally when you have something, you start with
会把
something
这个
positive.
因为这个
Very
里面的
much.
这个
And you do
然后
perturbations
这
here.
个
Means you
是
add small
基本上
corrections
是
to what you
新
had
豆
before.
腐，把这个
Small corrections cannot change the result.
对，然后我看你那个时候有太阳台
Yeah,
学
sure,
吧
like,，
你对它里面并不会
If you sum up,
找
it,
follow
but that's the question, how to
single
sum?
fence，你是这个感觉，我看我找下来我看一下我看
我可以把它拉上，可是
我读一下再问。
没关系。
One Q. You will
Maybe
not
you're asking you questions.
right?
I
So you basically want to find out what.
Yeah, I told you
happened
right.
to the
I
higher
know about
force, then
the sound
And then there's some.
in red in the sentences.
Yeah.
I saw
Yeah.
this statement about
Uh-huh.
when we turn interaction.
Okay.
Are we talking about the graphene one or?
How do you see that there are 3 channels? They do one thing, they do the three. Three different gaps. Sorry?
Why are these the right?
Say it again. Why are what?
Why are these three the right?
Why is this a three right?
Talking about.
This is something for you to do. You write down delta one, delta one dot, plus delta one times something, plus delta two times something, plus delta three times something. Right? Just
We are
we did
like the
for two ways.
simulation,
We do
the
the same
technique
for
will be
delta
covered
two,
tomorrow.
same like
All
delta
different
three.
notes.
Find diagonalize the matrix
Search the keyword.
and find out what are eigenvalues. These are, sorry, what are eigenvalues, right? Eigenfunctions, sorry, eigenfunctions, not eigenvalues. Yeah, this one. There's something to do. I cannot tell you how to do it in 1 second. You need to write down 3 by 3, diagonalize it, and then find out that there is, that for 2 channels, it will be this combination. For 1, it will be like this.
What would the matrix almost be? Like.
You calculate.
For example,
You calculate. This one will go like this. This one will go like this.
Some of like this.
Will go like that.
The
The point is that interaction.
Basically, think of it as like.
It doesn't matter whether it's a double line.
Homework. Right.
But through the interaction system, it's not exact. Was very cool.
Yeah, but it's
Two
low
interaction, 3 gaps.
Yeah.
But even not and the logs, you must still be there or it's logs.
Still there, I mean, because like the band is valid only in the single part of the picture, you think of them as like.
Oh.
If the latest question of cosine theta, cosine, sine theta, etc. This is cosine k x minus cosine ky. Expand here, cosine x minus.
expand your cake.
Oh, there's.
It will be cake by PY. This will be sign.
The other is.
Yeah.
Just. Yes.
Yes, well, anti-ferment is the same, it's
Oh.
in order to in the.
Oh, because I was like, when you said, what is it? I was like. And you said this.
Yeah, and some, I know it's a little bit confusing, for some people, index keyword is only incommensurate. But nowadays,
Because I'm thinking like.
I understand,
It's like
yeah.
alternating signs with meaning like two and plus one to state. It's like plus minus plus and I'm just like, I thought it was after.
It's anti-ferment, but again, nowadays, anti-ferment is also called equals. So, yeah, okay, it's.
Another thing, when you go deal with like four, it's also of twos because it's a spinner.
No, it's multiple of 4, because all we need, look at this, your dispersion should be absolutely symmetrical with respect to rotation of like pilot. There's only function assigned for that to do this.
Is each time I propose them periods, 4, 5 period and makes me suggest.
No,
maybe-
but this one and this one are different stories. This is square lattice. Right? This square lattice. For hexagonal lattice it will be 6 step.
6.
Yeah, because it's all rotations by pi over 3. Rotation by pi over 3 should be equal, so it should be 6 step. Yeah, this is why all the eigenfunctions basically are cosine 2 theta and 8 theta and whatever. There are more states. Yeah, this is why there are 3 different.
When we go on the mattress, we need basically nothing.
When we go to place, we don't have.
I see. So they don't sum up to a resolution of the event. That's the problem. Okay.
Yeah.
Okay. I think a question about, use it as this non-trivial phase value. I was wondering if there's some point for just not defined. Usually I think it would be not trivial phase value. Not so.
我觉得我奶奶找不到，反正我记错了。我如果有想说找到，他再问。
我猜你可能是在讲，
但你的意思是说，不管就那个，在这个行为其实不管你筛选，它的体质都是不一样。
对啊，但是 stage 我在传算，
OK，
但是 effective interaction 可能会变强。对，
就是因为它还在那个 stage，就是它需要跟那个就是存在。
不是，因为他刚不是说好，那我现在多少我做二阶，就他表现中间一次有搞一些的。Facebook 可以像在你来可以剑条。无限条，那我就把它写成 geometric series， 那就不要。如果分母那东西很大，或者会非常强。但是这个那个是跟有有关。对啊，因为你那个反正有一个 log 东西，对，那个 log 跑到我的 solution 跑，我觉得那个
Make a circle and don't go back.
它那边是拍是正比 log 或者拍正比 log， 那个东西跑到我的。
No, it's a solution with a solution from different topological sets.
我再把它丢进去。就变成
在
说那个漏的一个是有
对，
那你刚才外面讲那个
外面
在白板上面讲那个
白板哦，就跟那个 Brian 讲，
对，你讲那个如果那个话，你要写一个那个 log 怎么算？就是
那个 log 对是这样来的，是这样，你可以就是都算，比如说。cosine kx 加 cosine ky， 然后他们不要管那个因为说那边方面，就是一个单一的，然后你把它展开，我就做小我们的展开，所以 cosine kx 加 cosine ky， 然后那个变成这样子，应该小不了，所以就变成，因为你是对零派或是派零分，然后变成 kx 是零杠零2次，然后就是怎么。
这个就是那种你的文档有哪边有写的，有这个什么 nuance， 算过 explicitly 的，
有在那等一下，刚刚那个是 graphing 那边算到。
It's a phase which will start accumulating all the time.
I mean, you start with phase 0, it will go up, 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 and end up here. And then in conventional case, even if you do this, you can go up in phase and then it will go down. So here,
虽然说我们这边是用
or
in
in this
最
situation,
基本上就可以
you will
period
go down,
K
down,
K
down, down, and then
对吧？然后算进去，然后我现在就翻了 temperature，我要整 some more，
go like this.
然后这个图会变这样，这个是 identity， 这是 final temperature basically， 它就是differential functions。Okay. And then you integrate over over momentum. Then you get it at that divergence as well. Where the vector actually doesn't matter. At just 2 points is certainly variable.
First of all,
So you're saying the square
No, yeah, so it's the same story for square line, as long as like when you expand near the patch, you get something similar to the square minus 2 or square.
But look at that.
他说做一个coupling 的，还有他没讲这里，他用嘴巴讲而已，他没有说过，他就算 compensation 那些是我正常的。
So I'm wondering if we can already.
Oh, sorry.
So if.
I was listening to this. Yeah, so it's kind of get the picture of everything. You know what's happening when you take single kind of
Multi-divisible, you know. Ah,
So it's one chance.
this is interesting.
Yeah.
Whether
get either some kind of
fluctuations will
interactions
cancel out. I think they will, but they never did.
You could ask.
I think they will.
If I
I
take
think they
many
will.
different distinguishable molecules,
If we
put
want
them
to.
and pull that together. Or join that. And
You
that's
calculate particle susceptibility, right? With
Yeah.
overt interactions included.
Yeah.
And
I guess
simultaneous,
one
thermal, only
side.
thermal particles,
normal,
right?
The
And you also calculate, but you do calculation with the full grid function.
in this.
So every time when there's a line is full grid function.
Together.
And lines include
The density
thermal
of each atom is becoming really
self
small.
energy direction,
Keep shoving more
which
and
of
more.
course include,
Which takes
what
the
the-
scale
you
of
know,
where the.
when I say self-
down.
it's self energy, but self energy include thermal work.
Or it takes
Self
the
energy
actual
include
position.
Right.
So I think that's kind of. Oh, you start from 2PF and then
This
this
one.
one, so the 2PF goes to 0. This
So
PF.
include this
You're
graph.
at like the
Energy.
ultra low
Include
density.
this point
kind of-
graph for
Yeah.
the-
Well,
And then at low density, one fluctuation.
yeah, okay.
So we have to create. So you can.
What about you?
You can't do with A canals to E. And the reason for that,
Absolutely.
in A canal, the argument is
No,
this.
no.
It says, when you. That's the story. I mean, it's normally not so. What happens? Right? This-
Knowledge, symmetry based models, but trying to.
Now take one minute. This one is this case, this one is the
Well, it's like magnetic theory or.
This is your stat.
Yeah, I think like.
So you have to integrate over GQ.
Spin fluctuation.
Q, chi of Q.
Ball is like, for example, complex.
And then green function. So GK plus.
Oh, yeah, here's.
Have you read the
E,
books as well?
E.
Yeah. The first 2 weeks I was.
Is a line of symmetry.
And I had a weekly meeting.
And
It really
integration
like a-
comes from say. Five. Then you can pull out.
Comes collective.
From the-
Huh? Do we call comes?
For example.
Yeah,
suppose
it's
that
many
this
body
guy
based.
Strongly.
It's good, I like it.
Then to further
Very dumb
observation, you
question.
can write down A.
Why? What makes fermions heavy?
And you
Oh,
can
so
exactly the same.
basically. We firm
As a
you
result,
you have a local
get
moment.
at each
you
order,
have Heavy.
you get a
earth
number of.
atoms. That's why. it's
By
called
local moment, you
Which
mean
will
like
contain both.
static.
This one
Yeah.
and this one.
Static impurities, magnetic impurities.
Magnetic
If
impurity.
you do this.
So if you think about S
You
on,
will get in
spin,
both
right?
cases, you will get.
and that's not charged.
Green function.
But once
One,
it's surrounded by the surrounded connection
Get
electrons,
G,
what happens
K,
is that
some of them
it's
K, some of them K plus
or
two.
it's like screen.
I guess.
Yeah.
G,
And they
K,
form a
Q,
singlet.
K plus two.
Well,
Well,
once it forms the singlet, there's a
times twice
then
this.
it's
That's called A squared.
Wait, sorry.
And this graph, can be exactly.
So it's like one electron
So
plus
then
impurity.
each
Yeah,
one-
yeah.
Like this local one may have like large, I think like I said, like half.
Yeah.
Coming from-
If, but then what happens is that You have the.
And this, yeah, this you need sample using Barrett explanation. Because
And then the heavy electron, this like, for example, cerium, uranium, these are uranium 5F1, cerium 4F1, that's why we call it F electron, to distinguish two different flavors of light. Conductions can be neighboring or surrounding environment. That's
So
why.
the F1s are the localized electrons of
Yeah,
the.
yeah.
I know
Because
about
F
this
is heavy.
calculation.
Because you know the F1 is much heavier, and so it's localized, the potential is that these were also there.
But this, I like it because
That's
the
how I
base sort of tells you, yes.
Then,
Yeah.
once
What
they
it
interact.
really is that you assume that this is very similar. And two out from the green function from the, but if you don't do it, then I.
We have like the new operators, right?
Yeah.
Which is in terms of like the articles and all, and then here we have the same thing, but we have the mixture between SCs, and this is the heavy new
There's a paper, the last paper.
As if
So-
you have large mass or detected mass.
Yeah, and then what happens,
You can
because
go
of
down.
the original
down
F is so
to
flat,
so,
it's a flat F level,
2
and the
years
other
ago,
reductions
there's
just
more
dispersing, plus these
more,
hybridize basically.
there should be one with for
The
now.
F's kind of gain the charge of the C's, and then basically it becomes like a flattish but slightly dispersing new hybridized path. And because it's near tending flatter, it has a large effective mass. So that's why it's called heavy firm.
Yes, let's start with here it is. This is. So all discussion, all references are there. We are not different. It's a whole, there's a big literature. How to do this kind of culture. And you will see a lot of. There's one guy that wrote a book about it. Okay, guys. Yeah, sure.
I wonder what happened you can between layer and you get it.
Oh, no, come down. Oh, yes, basically what you do is this. It's like this. All you have to do is to write down condensation energy. It has, let's call it delta A and delta B. The quadratic order it will be delta A squared plus delta B squared. Okay. You cannot get anything else. Right?
Constant?
Sorry?
Constant?
No, there's no, you cannot get cross. No, because
Why? No constant.
you cannot get cross term. Because if it would be cross term, there would be definitely, how should I say it? Just one second. One and then, oh yeah, sure. You change sign of delta B and you change condensation energy. You cannot have.
Okay.
Right? So it should be even powers. But there are terms delta force. And you get delta A to force. You get delta B to force. You get delta A squared, delta B squared. But then function of cosine of the phase difference. So there will be a term something like this, delta A squared, delta B dagger squared plus complex conjugate. This term is allowed.
Right. It's like
This-
operating.
Sorry?
Operating.
Yes, it is like, but you derive.
Okay.
You just expand condensation energy in terms of work parameters.
Yeah.
And you just derive, nothing else.
Okay. I see.
Right, so when you do this, you get this term, and this term immediately tell you what the relative phase is.
Cosine of these two.
You see it immediately. The cosine of two twice phase difference comes in. And this cosine is either 0 or pi over 2 because cosine 2 theta is either plus 1 or minus. And all you need to know is the overall factor. Right, whether it's positive or negative.
Just make it an overall minus.
Well, you need to calculate the coefficient.
Yeah, I mean, equal you got just make it overall minus.
Overall plus, concession should be the last.
Sure.
Well, it doesn't matter, it depends on how you define it, yeah, how you define it, plus. Yeah, so this is how it goes,
Okay,
yeah, and it's very easy to do this calculation, really easy.
okay. If that somewhere already did it.
This was in the paper that we had with Levitov and with Rakul and Kishore back in, I guess, 2017. And this part is written there. So we described this calculation.
One very good comment.
因为怎么找你 Google 都找不到，因为我跑出来都是 FLO， 然后我不知道那是什么，那是 transport 用的。那个是那 equilibrium 就是有点像是